Alô, alô. Sim. Fernando me disse que...
Tinha que ser pontual.
Let's start for the last day, first session. And our first session is going to be started with my former student, Deniz. So I'm very glad to introduce you. Please, Deniz.
Thank you very much. Good morning, survivors. Not many left, right? So it was a tough night, so it was great. Thank you very much for organizing all this amazing thing. And just want to start with a little bit. I mean, I realized that showing pictures are amazing here, so I just wanted to show some. And with a goal, of course. So isn't it really awesome to be just next to cool people, right? And there is a recipe for this. The recipe is first, you find a cool mentor. You see? I mean, image is a little old, sorry, but probably if you use a little bit AI, you understand this is me many years ago in 2010. This is Uğur. And basically this leads you finding grant mentors, cool grant mentors afterwards, and Constantino Tsallis. So this is the first meeting where I met him in 2010, and then this is really amazing. So I know him like for 13 years. I'm very happy for this. But of course, I should show the rest, right? So they are also awesome. This is in Turunç. Then this is conference, Greek-Turkish conference on statistical mechanics and dynamical systems, run in 2010. And then we were these many people. And actually, this is the second one. I wasn't in the first one. Probably I was a bachelor student yet. Probably I'm still bachelor student here, but like senior. So, and this is how I met him. Then afterwards, of course, we met in many other conferences. Like this one is again continuum of this conference series. and many people here. Let me do a little bit showing for you. So what's going on? Everyone is there, you see. So all these good friends and so on. But you always want to be next to coolest, right? So Tiago is the most lucky one, in my opinion. But what I'm doing, I'm still steering at Constantino. So I want to be next to him, but not yet. So not developed enough, right? So for this, what we do, we invite him to our office. So this is my office in Istanbul. And but now in between there is a student, unfortunately. And some sneaky guy always taking these pictures. Who is this guy, right? So there you go. Then you say, okay, didn't work out in office. Let's go to holiday. And come on, now family in between. So this is my wife, Aytul, Uğur's wife, and Marisa, right? And you see, I mean, so there is always something in between me and Constantino. We couldn't approach yet. So problems. And again, who took this picture? Come on, yeah. So this is okay, let's try something else, yeah. Let's go home. We are having Turkish little breakfast. Now, not little, okay. Now my son interrupted. So again, I'm not really next to him. And as usual, Uğur. So thank you very much for all these good memories. Yeah, so you really in our lives, Constantino, and thank you very much for taking us here again. Beautiful city, Rio. Okay, so I also need to say something about science, right? So I'm working on dynamical systems. So actually my career started with Q statistics when I was in bachelor, when I was a bachelor student. So I published a paper in the field. Then afterwards, Constantino's good friend, Henrik Jensen, and Uğur drove me to some different direction, which is dynamical systems more, and then try to understand the dynamics and then stabilities and so on. So instead of the statistical mechanics part. And then life somehow put me into, from this very theoretical research into data science. So now I'm trying to blend data science and dynamical systems. And here I will show a problem about inverse problem, which is this. So we do have some system, and then this system has some nodes, like these parts, and technology is well developed, and then we can probe data from these points. And then data looks like this coming from these nodes, right? And then this is we call data time series, whatever you want to say. And main goal is to predict critical transitions when these guys will change their dynamical behavior. We want to understand this from data. There are some machine learning techniques. What you do, you train your system. After you train your system, try to understand. So if I basically check the behavior in future, what will happen? This is good, this is cool, but there is a problem. Machine learning can only learn what are the current parameters. If there is a parameter change, then whatever machine learning learned, not useful anymore, so it's useless. So which means making prediction directly from time series, not really the goal for our case. So what we want to do then, we want to learn the model, which means we want to learn examples like these neuron networks, climate networks, and so on. What are they? Like you just basically probe your data, but you do not know what you have in the background. So how these guys are interacting between each other. So from data, we want to learn this guy's isolated dynamics given with F. We want to learn the graph underlying G, and then how these guys are talking to each other, which is called coupling function H. Yeah. All right, and I will skip this part a little bit quick, just showing few results. Then come to my main goal for today. Selected example is brain today, and brain is a thing, and you do have some different areas, and then these different areas controlling different functions. Some of them controlling like this motor functions, some of them some other things, and so on. And they need to have some synchronization internal these regions, and maybe sometimes in between. This is all neuroscientists saying that. But there is a region which is called Rich Club right here, connecting all these parts to each other. If there is synchronization in this part directly, then this is a pathology, for instance, epilepsy. And our goal is we want to take neurons data, reconstruct network, and then if there is synchronization in this Rich Club, in future or while parameters are changing, we would like to detect this, predict this. So, and then how we abstract this brain into networks. So we basically have these parts, these blue things, they are the parts. And then this part is the hub connecting everywhere. We put our oscillators on it. They are basically running, we are running neuron dynamics. And afterwards we collect data. Then we forget about all the dynamics, all coupling function, all network topology, and reconstruct it. And we studied this problem with some mathematical techniques, tools, plus some machine learning. And this works like this. So we get time series, we have some local dynamics plus coupling. So which means it's very hard to learn one by one everything, but we do some tricks. And then to do this, we developed a technique which is called reduction theorem. So reduction theorem simplifies, using mean field theorems, simplifies the dynamics on each node. And this, after learning this dynamics, we do have some fluctuations. In general, these fluctuations are not super big. Then afterwards, we can go to each of these nodes with this reconstruction. It's doable afterwards, and then apply a sparse regression machine learning technique to learn which guy connected to whom and so on. So, straightforward regression methods. And then this reconstruction theorem, so published here in this first paper in 2020. And we use machine learning technique of this famous Terence Tau's sparse regression basis procedure. Then we do this, we learn network, very good. Then afterwards, we have the model now. After having the model, okay, we try to then generalize this thing. So what we have done, so we added some noise, and then we try to understand if our technique is robust. Also, if we have noise in the system, then it worked very well too. And then very recently, with my student, we published it just a few months back. So which means if we do have access to every single node, we can basically get this data, learn the model. After learning, we can do the modeling. And then if we can do the modeling, then the rest is already done. So we studied this. For instance, if network is like undirected network, we studied this in this paper. So we know how to predict critical transitions. If network is heterogeneous, we studied this in 2013 together with Ur and Henrik and Tiago Pereira. Now he's at USP. And then if matrices like networks are represented with non-normal matrices, we studied in this paper, published again previous year. So what we do, this is coupling strand. This is synchronization parameter, order parameter R. If R is 1, system goes to synchronization. And what we want to do, we want to learn the system when coupling strand is small. This is the data. You see there is no synchronization. We learn here, we reconstruct model. We apply these prediction techniques. We find where the system will be bifurcating. And afterwards, we do these simulations for different parameters. Then we really realize at this point, system bifurcates. And then this is like analytical results. This is very good. So which means if we have access to every single node, and then if we have nice data, we can do this. This is really shown now so far. But the problem is this. Whenever I talk to a neuroscientist, he says, you are living in a dream world. So this is not reality at all. Because there is an assumption which will not be true for a really long time, which is you will have no chance to get data from every single node at all. So you can only have maybe mean fields using this EEG techniques and so on. Then, okay, challenge accepted. We started to study this problem. What we do, instead of having data from every single node, we say we are learning, we are basically probing data from these mean fields. This can be considered like a EEG signal, like sensor. You take data from this mean field, and this comes as like an amplitude and so on, and then we can write them in like phases. And this is my basically for each system's dynamics, phase dynamics. And I want to learn the network, but this is impossible because I only have one node for here. Then what I do, I basically design my network interacting mean fields in this way. Then this is the coupling term for this system, basically linking these clusters given with L. Okay, nice. We have a nice model. And what we want to do, we would like to again write this entire thing in mean fields. When we write it again, so then this guy becomes this thing here. Then afterwards, we know another technique which is called Odd-Antonsen ansatz. We can apply this thing, then our system becomes into this form. And then this is given now with complex space, in complex space. Okay, very good. So we want to study synchronization and then brain and so on. So what you can think, I'm going to show now. We want to study synchronization, and the synchronization means we have phases, and then their rhythm will be like synced. They will basically rotate together. Yeah. So if everyone rotates together, what I can do, I can counter-rotate the frame, which means synchronization is a fixed point. I can define it like that. If synchronization is a fixed point, and then auto-synchronization can be considered like a rotation. So which means from fixed point to rotation, which is hop bifurcation, right? Then F is hop bifurcation. So I select F as a hop bifurcation normal form. Then afterwards, I use some standard parameters. Then if I have linear coupling, so which is the case in general for these neurons in electrical coupling case, then this coupling becomes into this form. This is nonlinear and interesting actually. So I didn't know that. So I was basically showing this result in a math conference very recently. And the guy studying PDEs, he said, so do you know what is this coupling? I said, not really. And he told me that this is really the coupling seen in Schrödinger equation, as far as I understand. And I didn't know that. This is just basically appeared into this reductions and so on. But people were really interested in seeing this. Anyways, that was only for chance, by chance for me. Then what we have done, so we put all these things together, and we wanted to satisfy some resonance conditions. So since we want to see synchronization other way around, so it's very hard, then what we put, there are two synchronization, resonance satisfying conditions. Like these guys are more or less same. So if you sum up these two guys, omegas, and then giving these guys, yeah. So this omega 2 equals omega 1 plus omega 3 and so on. Under these conditions, they are just basically cooked up. I run the simulation. I get such a thing. This is in complex space. And these are my parameters. And then you see, so I'm only like wiggling around my circle. If there is no coupling, which means all these colorful trajectories will be on this line, radius, on this circle. And I can unwrap this thing and then show them as phases, as in the beginning. Then I can find how these guys are growing. And then if I remove this growth term, then I only have this flat fluctuations around. If I reconstruct this, then this will give me back the original starting point, this ring topology. Then what I need to do, I just need to solve this equation, linear equation, quite simple. how we solve these kind of equations? We have these phases. We take their derivatives numerically. And then we say, here is the network structure will be appearing. And afterwards, we create our library function. And then this library function contains like constants and harmonic terms. But up to order something, maybe 4 or 5 something. So you see, coupled like 3 oscillators here, and then we use more. But second order is, so 2 oscillators, coupled cases here, single oscillators, like trigonometric functions are here. They are all here listed. Very big library. Here is data. And then when I do this regression, then I expect to see network topology here. Cool. And then I can write this into equations. When I write it and then add this growth, so which means instead of this slow phases, I go back to this again regular phases. And you see, so this is the omega I put already. Fine. Then the rest of the system appears like triplet interactions. But I know equation in original pairwisely interacting. So how can it be possible? Then I studied this problem. So why this reconstruction gives me hypergraphs instead of original network? Since all the parameters of this original network was also into my library, right? So should be there, but not. Only this one is coming. Then I wanted to understand this problem and then went into this equation back. I just basically thought this. I'm using this ternstau basis proceed, compressed sensing. And then compressed sensing is trying to reconstruct the sparsest form of the system, right? So this is well known. Then if I am looking for the sparsest version of this thing, then what I need to do is the first thing, maybe true, maybe not, but I can look at the normal form of this gigantic equation, which is well-known technique, but a little bit hard because we have like many things and so on. What we do, we apply first coordinate transformation to find out the normal form of the system, and for some polynomials here, then I fix this part, and then there are no like second order terms anymore. Whenever I apply this, there will be some third order and so on, like which means 3 coupled oscillators in my equation. Very good. But whenever I do this, then I break this one. So you cannot do normal form one by one. So you have to apply to every layer. Then now second, two coupled systems are coming from this guy. But this is already super long equation, yeah? Then afterwards, I apply another normal form theorem to basically get rid of all this interacting 2 units with respect, so coming from this equation, coming from this function. Another coordinate transformation, then it becomes a mess, really, but you can get rid of all these pairwisely coupled elements, and then you only have higher order terms. But of course, this is becoming really non-trivial combinatorial problem. Then we introduced a special bracket, which is very close to like Lie bracket, and then using that, we managed to find out for each system which guys should be resonant terms staying, and then which terms are non-resonant, and then we delete. So we became with an algorithm to do this. Then afterwards we could code it up. So you just basically give your system, which is available online. You give your system, and this code computes which terms will be resonant, which terms won't. And this is the formula for this. If you have like these 2 resonant terms interacting in this way, yes, we keep it in our pocket. If this is the other way around, same thing, we put in a pocket. But if this guy is coming like that, then we say they are non-resonant. So these blue ones. So which means we trash them from our equation. This is also resonant. You see these oranges are so coming in at the ends, but this is forbidden because this is not in our own network. This is not really the original system link, this red one, going from 2 to 4. Normally 2 to 4 is not connected in the original system. then which means we drop this guy as well. So after applying all these things, all this algorithm, then we realized this system, normal form, is really given with this equation. And then this is the normal form for it. And if we basically define this new psi for like only two oscillators, because we do have only these two types of coupling, this purple one and then the green one. So they are coming from data. And then our normal form really estimates this. If you zoom into this part, then you see blue, green, and this purple parts are oscillating super fast. But our reconstruction finds it's only envelope. Yeah. So this is basically the sparsity. Sparsity brings this to us. And then we realized, okay, boom, problem solved. But again, people say, so this is only on like your equations and then like simulations and so on. We need an experiment for this. I talked to a friend from St. Louis University, Istvan Kes, and he prepared such an experiment. I'm really bad with experiments, so I do not know what he's really doing. I'm very bad also in kitchen. So I agree with Constantino yesterday. So I'm very happy to be in the theoretical part. But this guy, since we have this complex system, right? So complex oscillators. And then this is not a complex normally. So we need like the imaginary part of the system to do our tricks for the coupling and so on. And this smart guy introduced some delays. And then with this delay functions and so on, he really managed to construct exactly the same thing with this experimental setup. Then this is, you see, our network, exactly the same network, like ring network. And we take this ring network here. This is basically data, voltage is coming from here. Then we do some smoothing, and then we compute again the derivatives, and we compute we apply our algorithm on it. Then we really reconstruct the hypernetworks. Then the mystery is solved, and which is published in last year again. All right, and I promised to say something about predicting critical transitions. Because of that reason, another example cooked up. So the coupling term now like this, simpler, only quadratic. And we have these oscillators here with these parameters. But here, interesting thing, this coupling is not diffusive, which means oscillators are not following each other. So they are basically repelling each other. And then in this case, normally you do not expect to see any synchronization. They are not really running after it. But if you apply our theorem, then you realize this system becomes into this hypernetwork with a master slave form. You see 1, 2 drives, this is the drivers, this is the driven node, drives this. And then this is really the mechanism for synchronization. Then afterwards we realized, so we basically did this simulations. Here's delta, mismatch parameter in our oscillators. Here's coupling strength alpha. And then we did the simulation. And then according to theory, with this master slave system, there should be a synchronization. And then we found the Arnold tongue, but which is non-linear, which is not linear anymore. Since coupling is non-linear, right? And basically, that's it. So, but I have to say something for Constantino. I was traveling, so because of that reason, I couldn't come directly from Turkey to here. I couldn't bring you any present. And then I didn't want to buy something from here, right? So this makes no sense. Because of that reason, I wanted to do something for you. I am not really only reconstructing brain or some similar things, but I also reconstructed your publication network here. This is like just a quick present for you. So here is you, and then these are all your colleagues here. I'm here. You can find your names probably here. And these 3 red nodes are your mostly published collaborators. So our champion is Silva. Yeah, you are the champion. Yeah, yes. Yes, yeah, basically you published the most paper with Constantino. Second, Fernando. And third, Uğur. Oh, definitely, yeah. So I can do better one for you. This is what I learned in Rio. Without money, you do not do anything, right? So no. But I do have a better surprise for you. Even better. Your Q is 1.2 for degree distributions. This is degree distribution. This one. This is basically people who has 2 publications with you. This is 2. This is 1. I mean, so if someone has with 1 publication, you have like basically 17 people. This is with 2 publications, something, and goes like this. This is scale free, and follows Q Gaussian with Q equals 1.2. Q exponential. Sorry, I'm sorry. Yeah, you see, I changed the field, but still I do have a paper with Constantino, which is very recent. I would talk about that work, but I thought maybe it's better Henrique will talk about it with you, since he is our young star, so he should talk about this work. Because of that reason I skipped. Henrique is there. If you wonder what we have done together, Constantino, Henrique, and Uğur, please talk to him. And then he had a poster yesterday. I hope you saw this brilliant poster, but he might tell better what we have done. All right, thank you very much.
The red positions is the same as the other, just you took the 3 highest numbers.
Just to represent, actually.
I see.
Just for representing. No, they are just randomly distributed.
Oh, no, I was just asking, how is this organized? Because I see everybody's name, but I don't see my name. So I was trying to.
It must be somewhere.
Yeah,
I can make you red as well, yeah. So
More questions?
Okay.
Web of Science or from
I
where?
took this from Saivel, the Scopus, I guess.
Scopus.
Yes.
Very nice talk. Thank you.
My pleasure.
Have you already tried to infer the network of protein-protein association?
We started somehow, so we have some results, but not really network-wise. We just try to understand if we have this single cell data and the sequencing data, and then if we have also this spatial transcriptomics, can we make some understanding between these 2 things? I guess next step will be the networks. So
yes.
we just started this.
But you will have problem with the noise.
Yes, but the thing is the following. As you do the sparse regression, even if you do have noise, we only look for the envelope of it. Because of that reason, this technique should be robust against noise. That's why we published this paper this year with my student in PRL. I showed like this technique is quite robust against noise.
Okay.
Hopefully we will not have problem. Yeah, we'll see. So we never tried yet.
Okay, if you have, you talk to me.
I mean, if we have a problem, I will find you. If I have a problem with noise, I will find you. Yeah. In the pocket, yeah. Yes, so there is an algorithm behind this, like a spring mass model. So if they are like too big, then they repel each other a little bit, because I wanted to show you without any overlaps. Yes, so but look, so this people, they only have like 1 publication with you, probably this surrounding. So because of that reason, kind of, I don't know, Lena Jones potential, like, right? So they do not want to be very far, but they do not want to be very close. And then big ones, they repel a little bit more, but keep everyone around it somehow. So this is an algorithm. So I didn't write this, somehow used automatic generator, but it does this. But we can try different techniques, of course. Yeah.
That picture
Yes.
on the right hand. No, I mean your curve. Curve.
This one.
Yeah, the red one,
What red ones?
the red side there. See, from longer till now.
Ah, okay. This is probably like with the, yeah, like one publication with like 20 something is Silva here, this guy here, and then probably Nobre is this, and then Ur probably will be in this community. Okay, maybe I need to tell you another thing. So this is basically all your papers, but in your papers, so somehow like people can be also collaborating between them, right? So because of that reason, these red points, they do not show the largest community, the largest K. So for instance, Evaldo is here. Probably you have many papers with Evaldo, with some other people. Because of that reason, degree of Evaldo larger than Fernando. But Fernando has more papers with you than Evaldo. Yeah. Q value, yeah, Ur found it for me.
You can do something like that with citation.
I can do everything, yes, sure. Network is my business. Sure.
Thank you very much for your interesting talk. But I have a question about, comparing your work with what is usually done, which is to look, if you want to reconstruct the network and do a network from the original time series, to just look at the time-dependent correlation function, like for instance, Dante Calvo does. And how does your method compare to this traditional method, let's say?
Okay. Let me do, no. Okay. Okay, you saw Suarez on me, right? Okay, no problem. I skipped tons of slides here, but when we choose this neuron dynamics, coupling is very small and then super chaotic, fully developed chaos. And if you measure the correlation between these oscillators, so you find basically nothing. And what we do, we tried everything like mutual information and so on, all the similarity things, never works. And we have some like assumptions. Let me skip them for now. And then this is the reduction theorem. And after applying this reduction theorem, we learn all these deterministic parts. And then afterwards, there are some fluctuations. Actually, in turn, this broad term like kills the correlations, but these fluctuations learns the network structure.
Thank you very much.
My pleasure. Yeah, sorry. So I had no time to show everything, but if you have more questions, we can, of course, discuss.
A little remark. If you take in that equation alpha equals 0 and f a sum of a linear term plus a quadratic term, which you did in one of your equations, but with a minus sign, with a minus sign in front of it.
Okay.
This leads you to Planck law.
Yeah, you see,
black body.
another thing that I learned. Yes, maybe. Yes. Good. Yeah. Cool. Yeah. So this was also surprising. Somewhere else, I learned this function for Schrödinger now. So this Planck law. Yeah. So probably we do something really around this nice physicist, right? So this is very cool.
But you have to take out equal.
Yes, I understood. But which means there is no coupling anymore. Then there is no network. Yeah. But still cool. Yes.
Okay. Any other question? I think no. So
I'm done, I guess, right? Thank you very much.
okay, the next speaker. Huh? No?
No. I need to show something. Since the achievements did not finish here, right? Finally, I had a picture with Constantino next to each other.
Yes, yes.
I managed it. Okay, now you can take my off. Thank you.
Okay, now the second speaker is my dear friend Celia Antoniodo. And
Ay, no. Hello. So first of beginning my talk, I wanted to take the opportunity to remind some of the works we have done together. I saw that the first one was about turbulence in 97. It was based on a recent experiment, but at that time, on turbulence on pure electron plasma. And with the extension of Constantino, we managed to describe better, in that case, the density profile in meta-equilibrium state. Then we worked on long-range interactions. This was very important for me, very cited work, and gave rise to many extensions and collaborations. And I worked a lot on this subject later. The main result, Rapisarda, I think it's not more here, but the first time he has talked about this extension of the so-called Hamiltonian mean field to arbitrary range of the interactions, where we have shown the dependence, the sensitivity to initial conditions depending on the range of the interactions. And then this is the result that summarizes this. The exponent shows that in this region for a short range, the system is chaotic, while it decays with the system size, the Lyapunov exponent, for sufficiently long range of the interaction. This is a result that was obtained numerically, very hard at that time to reach large sizes. But then this result was shown analytically with the random matrix in a work with Raúl Vallejos. Tamarit also, we made an extension later about the phase transitions in this same kind of system. We worked also on econophysics. Some works were related to the fact that the high frequency returns, for instance, follow nicely the Q-Gaussian distribution, very far from the Gaussian, which is dotted here. So there are some works that are related to the stylized facts. And there is also a nice work about risk aversion, how it affects the dynamics of economic transactions. I think that Alexandre mentioned this work 2 days ago. And it was a very nice, very hot subject. In the same year, Kahneman, which had proposed this extension of the expected utility theory, won the Nobel Prize together with others. We were working before knowing he was candidate to Nobel Prize. And there was an anecdote related to this work. Constantino presented the work in Indonesia. And we had in the conclusions a sentence saying that some level of cheating avoided extreme wealth inequality. And so Constantino was asked by journalists after the talk if Indonesia shouldn't pay the external debt. I don't know what was the answer and what happened after that. But it was funny because it was only a conclusion of our model. We're not claiming to be a general conclusion. We also worked on multiplicative noise systems as a possible mechanism leading to non-extensive statistical mechanics with additive and multiplicative Langevin equation, where we derived the extension of Q Gaussian distributions. And also there are some words, many words that were not perhaps directly related to non-extensive statistics, nor done in collaboration with Constantino, but motivated. For instance, Angel, I don't know if here, but this motivated to introduce another extension of another entropy based instead of the Q Gaussian in the stretched exponentials that are also a very important family of functions, not so successful and with the validity of all the properties, but we checked that it respected most of the requirements for a good entropy. So in this respect, I want to thank Constantino for all what I learned working with you, and also the very nice moments until tonight also. And so Constantino, happy birthday and congratulations before I start my talk. So I will talk about recent work I'm doing about quasi-equilibrium states. This is the official subject. I had given the abstract. And just to summarize what it is about, the idea is to consider potentials that are confined in some region. This is the scheme of the potential, where there is a confining region, but the potential is flat asymptotically at long distances. So for this kind of potential, if we try to apply Boltzmann statistics, of course, due to the fact that B is 0 is far away, the usual partition function will be divergent. But what we observe when we put a bundle of particles more or less inside the potential well in the region where it is locally confining, we observe that there is an stagnation of most observables. For instance, in this case is the mean square displacement, but we can also consider thermodynamical quantities like entropy, energy, etc. And this stagnation region, this is a transient stagnation, what we call quasi-equilibrium, that can be last long periods of time depending on the temperature and the potential depth. So, but the usual statistics does not work. But what we show is that to calculate the average value in these quasi-equilibrium states, we can still rescue Boltzmann statistics, but we must make some kind of regularization to avoid the divergence of the partition function. This is the idea. This is all. So the question is how to calculate these values, and the answer is using the regularized form of the usual statistics. So I will try to show you some details. The kind of the confinement and non-confinement that we are considering is common in many interaction potentials and Lennard-Jones or Morse. But what we are thinking in this case is as an external potential, where there is some region that is confined by maybe optical tweezers or maybe some membrane that or substrate that close to it is attractive, for instance, but far away in the case with distance. So there are some experiments that where there are this kind of interactions or effective interactions where we see, in this case, also the square displacement, that as a function of time, depending on the parameters, shows this kind or tends to show this kind of stagnation. So this was the motivation to try to obtain an estimator of the mean values in this state. So what we consider is Brownian particle dynamics, where the force is derived from some potential with the characteristics I described, and we use as paradigmatic example this kind that in some words we are not referring to Constantino statistics, but there are some footprints like this that is a Q-Gaussian form for the potential. And the potential does not need to be with a single minimum. For instance, we can perturb. The important thing is that there is a localized region where it is confined. So this is the kind of potentials we use it as paradigm. And this form is interesting because it can allows us to change this exponent, the degree of flatness of the potential at long distances. So we used to describe, to make analytical calculations, the associated Fokker-Planck equation, and scaling the variables, we arrived to a form that depends only on a single important parameter, that is this psi, that is the relative temperature, the temperature relative to the depth of the well. There is also, of course, this parameter that rules the decay of the potential. So for this equation, one calculate mathematically the stationary solution. The stationary solution is Boltzmann, but as it's obvious this is divergent. But it will play some role, despite it's not normalizable. So numerically, we can solve the Fokker-Planck equation, and we observe this kind of behavior for sufficiently low temperature, okay? And this may be very long the lower the temperature. So what happens, to understand what happens, is relatively easy if we put initially these particles in the central region. Doesn't need to be a delta, but more or less the bottom of the well. What will happen is that the particles will diffuse initially. No? So we will see for the square displacement as a function of time, the diffusion law, linear law, and at very long times, most particles have left the well, and also we will see a normal diffusion since the forces are tending to zero far away. But it is at intermediate time where something perhaps not so obvious may happen, and is there where is the region we must solve to obtain information about the almost stationary states. And if we think, we keep in mind this picture, it's natural that in the first times where the particles are in the bottom of the well, they will not see the non-confinement at long distances. And then the Boltzmann factor will give a dominant contribution to the probability. This is why this factor will remain in our solutions. But far away, there will be some kind of cutoff. So as a first try, heuristic proposal would be to think in a solution that has the Boltzmann factor plus some kind of cutoff, and the cutoff will come from the solution of the diffusion equation. So this is to match both parts. We propose simply a product. This error function, complementary error function, is almost 1 for small values of x, and this exponential is 1 far away. So the simple product works relatively well to give the solution. I will not enter in details, but we have also solved the solution approximately, but with more care, using an expansion in eigenfunctions, with close to find this simple heuristic expression plus the corrections, but we will consider the simplest form. There is a correction in the complementary error function. There is a phase. In the Boltzmann factor, there is also a correction that depends on time. But to show you in which this regularization is based, I will use the simplest form. The idea is to calculate this constant, this normalization constant. So what we do, we integrate the expression, and using the property I mentioned, this is one far away, this factor is one close to the origin, then we can split the integral into parts, one up to a certain L point of crossover. So we have these two integrates, and now what we do is just to add and subtract terms in order to separate some part that is time independent. So what we have is that adding and subtracting terms, also to have integrals that go from 0 to infinity. There is a simple correspondence, but I want to take time to show this in more detail. What we have is that there is a term that is time independent, and it is very dominant in, if you see close to the origin, this term b minus b is close to 1. So this integrand is order exponential 1 over psi, and if psi is small, then this is very large. There is also another integral from 0 to infinity that corresponds to the complementary error function, and we can do this integration exactly. And there is an intermediate term that is negligible. This is almost 0, the integram. So what we get is a term that is time independent, that it is what we are looking for, and a term that depends on time. So this is a very large, can be very large. So for times where I can neglect the time dependence, we have the time independent solution we are looking for. And we have the solution, and also we can get from this expression the order of the time scales where the approximation is valid, which is related to the duration of the quasi-equilibrium states. So this expression has this form. So this is the form of the regularization we are looking for. We cannot use directly the Boltzmann factor, but if we subtract some terms, then it gives us the proper normalization. In the case of the square, any average we do, we will need to have to perform a similar regularization. If we want to perform the average of if a square, this will contribute against the divergence of the integral. So we will need more requirements. This regularization that we applied in the case of the norm will be valid only for potentials that decay faster than in the previous case, like a third power of the distance. So in this case, we obtain an expression for the square displacement that describes very well the exact numerical solutions. If we want to obtain an expression for potentials that decay more slowly, then we will need to add more terms, subtract more terms, and we have a general expression in that case. Here is, for instance, the case where the potential decays as 1 over x, where we need to correct both the norm and the integral involving x squared. So we have to subtract more terms depending on the observable and on the decay of the potential. But in all cases, this expression works very well, as you can see here from the comparison of the continuous lines are the exact numerical solution, and the dashed lines are our prediction. So we have checked for other observables. Depending on the observable, the quasi-equilibrium state may last even longer, as in the case of the energy, or also the entropy for the same value of the temperature. And well, let me check. There is also another approach we can use to understand the problem, that is what we call the bounded domain. Instead of considering the original potential, we can add a bound, and in that case, the system reaches a true stationary state. And to recover the result for our problem, what we have to do is to move the walls. And doing that, of course, we will arrive to the same regularization. And here is the previous picture I have shown to you, for instance, the square displacement as a function of time. And here is as a function of L, the width of the half width of the distance between walls. And we see a similar relation. This is because the distance is related to time due to diffusion. Okay, so I am cutting some things. Just here is a summary for the case of the square displacement, where we show as a function of the relative temperature what happens. This solid line is the numerical value. This dashed blue is the harmonic approximation. We can simply fit the bottom of the well, approximate it by an harmonic function, and it works for very low temperature, but you see it doesn't work, or better than our approximation, which is the approximation is the solid is the log reflection. Okay, I don't remember now which is one, but they are very good, these two. And this is this red is simply an approximation of the analytical expression we get for very small seeds. It's an approximation. Even it is better than the harmonic one. So we have also worked with some variants with anomalous diffusion. I will not show the details now. I will pass to the to the summary. So we have shown that for this kind of asymptotically flat potentials, we can use Boltzmann-Gibbs with appropriate regularization to describe the quasi-stationary states. We obtained rigorous results for the problem. I have shown to you just the simplification, an approximation which can be understood heuristically, but we obtained more rigorous results. And here is not said, but in the case of the anomalous diffusion, we extended the Fokker-Planck equation to the case where the time derivative is fractionary, and this leads to subdiffusion. And I don't have the result, the summary for that case. Ah, yes, here it is. In that case, as it is subdiffusion, the quasi-stationary state lasts for longer times. But there are still many things to do to study the relaxation properties, both to and from the quasi-stationary states. Variants with stochastic resetting may be interesting too. There are, we have studied this extension of fractional time dynamics, but there are other extensions. Perhaps there are extensions using, for instance, the nonlinear Fokker-Planck equation that may lead to Constantino statistics, and hence where probably a regularization is also needed. And what we are working now is in the interacted particles problem. In this case, particles are subject to an external potential, but it would be interesting to study what happens with this kind of potential for interacting particles. So this is all I wanted to show. And again, I want to congratulate and thank Constantino. I hope that it is correct. So. Correct.
Thank you very much, Celia. Questions, please?
Yeah, thank you for your talk. When you have, for example, a potential and you have a very small temperature, you have a relation in this temperature and the height of the potential before it goes to zero, né? And this implies some kind of time scale, depending on this relation. Né? If this time scale is so large, you can treat this as a really equilibrium during that time, no? I believe you have an estimation of the time with respect to this ratio.
To the rate.
Temperature.
Well, yes, there is a relation that can be obtained just from this first expression. Here you have this zero is related to the relative temperature, and here we have an exact expression. Is simplified, but we have the exact expression as a function of time, and this will give us the duration, the time that most particles are still inside, and you can estimate from this the characteristic time that particles start to escape from this relation.
You have not written the relation with time with this ratio, no?
No, and it's not explicit, but here you
see,
you go back.
Here,
yes, here this is practically order proportional to the exponential of 1 over c over psi. So we have a relation out of a prefactor. It would be related with Arrhenius time, but the problem is not the escape over a potential barrier, but some proportional time appears here.
Okay, more questions? Seems not, so we thank again. Now, the next speaker is Andre.
Eu andei desde ontem. Eu andei desde ontem. O rapaz está lá. Oi? Não, eu mandei apresentação para ele ontem. E ele não achou. Não. PDF. Okay. Good morning. I would like to thank the organizers, Fernando, Evaldo, Hans. It's a pleasure to be here now. Thank you. Okay, I met Constantino 32 years ago. I was a student. Here is my master thesis. I finished in 1993, and my PhD degree I finished in 1997. It's the committee. And here is my first paper with Constantino and Ananias, my second with Tamarit, and here in my master degree, and for me, my principal paper of my life, on my scientific life, was with Constantino. It's about Levy distribution, and here we won the prize of physical society, Brazil society, the best PhD thesis with Constantino. And after then, we work with about magnetism, memory effects, stock markets, diffusion, Weierstrahlung radiation, you remember? About Planck equation, superstatistics, nonlinear Schrödinger equation, and finally, and my last paper with Constantino was about entanglement, and my last, but so far. And for me, it's a great honor work with Constantine during these years. And for me, his intelligence and ability to work as a team are a reference for the science. As a team, we can see the network of Constantine. It's very important. It's a reference for the science. Okay, Constantino learning physics, not English. Sorry, but my horrible presentation. I prepare especially for the birthday of Constantine and a simple problem, and I use a two-level quantum system. It's easy, it's trivial. You can see the two-level system, quantum. Here it's a diagonal Hamiltonian. We have two energy, okay? But of course, if you use a thermal bath, we use a Boltzmann-Gibbs in principle, and you obtain the probability of we find a particle in each level. Okay, it's easy, it's trivial. And now let us study general case. Okay, now the Hamiltonian, no more diagonal. We put a new term, a non-diagonal. Oops, a non-diagonal term here, and I use three parameters: lambda, z, and delta. Okay. In this case, of course, we have new wave functions.
You can call it lambda z, you can call it z prime.
No. Oh, you can see okay, because we change the lambda. Okay. The next we can express the ground state like eigenvectors of the diagonal Hamiltonian. Okay, it's easy to remember. And now I solved the simple problem, and I found the ground states, and here we expand the ground states in terms of the two non-interact states. The ground states of the non-interact states and the excited states. Here we assume alpha and beta equal for the user, only the case where these terms are real. Okay. In this case, of course, you remember that it's a quantum problem, and in this case, if you use the ground states can be expressed about the probability of found the particle in the ground in the wave functions of the of the diagonal Hamiltonian. This is the important in the easy to see that the probability of occupying the excited or the ground states. Sorry, it's the ground states. Okay, and we use the next the inverse relation. It's what is important for us. Okay. It's easy to obtain these two expressions. Okay. This slide is very important. Very important. We can define an analog of the absolute temperature scale. Okay? We use this relation. In thermal bath, we have a temperature, and with each temperature, we have a probability of occupying the zero base, the zero quantum state. And of course, if you don't have temperature, we can express the ground state of the quantum problem in similar manner using now this. Oops. This probability. Okay. And in 1970, and Fernando D together, we published a paper using, and we introduced a ground state thermodynamic, defining the ground state internal energy, ground state free energy, ground state entropy, and but now we observe that in this define, this average is a quantum measurement. It's not a thermal average. It's a quantum measurement using the ground state. Using the ground state. Here we don't have temperature, but we express and we can found a similar, an effective temperature. Okay. Oh, it's okay. We easy to see that this the energy, the defining energy, we express of this equation, and now we have two forms of energy exchange. We have two forms of energy, and now we can associate each term like heat, where we change the probability of occupation, and the second we identify like a work, where we change the gap between the two energy level. Okay, and now we identify a first law, thermodynamic first law, And here is important, we identify the relation that we obtain the effective temperature. The effective temperature. Now, in sequence, we found a relation between temperature and the parameters of the previous, the Hamiltonian, and now we obtain this expression for the entropy. For the entropy, it's okay. A constant we obtain analogous to the standard thermodynamics, potential thermodynamics, response functions, Carnot cycle. It's simple to obtain. Okay. Similar results of to the above formalism has been found for a model of interactions bots for type 2 superconductors. We remember. And a non-additive entropy forms, and an appropriate effective temperature emerges as an appropriate framework exhibiting properties very similar to those of the usual thermodynamic temperature T. In particular, for the VEX model, the entropy is SQ equal to 2. And it is the reference. And the question now. Yes. Okay. Remember this relation, quantum and thermal, and the question now is, given an expressions of P, the thermal P, it's possible to obtain a quantum equivalent. This is the question. This is my answer. This is my work here that I present for Constantine. Yes, yes. Let's see. We follow the Clausius approach. It's possible to define the entropy. And now this is the Clausius approach. We remember that the expressions of the heat is oops. So in this situation we change here and we use this equation, and remember that we use theta, the effective temperature. It's a function of P, and now we only change and you use the inversive functions of G, and you put here and you obtain this expression for the entropy. And we remember that we invest the functions of P, and you can put the inversion. Like now I use, you remember that lambda of the Hamiltonian Constantino, lambda now is F theta. Lambda is here is the principal result of this work, because we use okay. Remember that lambda, it's a parameter like interactions, for example, and we remember that this is the P, and we invest and obtain this equation. And now we have a protocol. We have a protocol, and the protocol you choose a functional form of P, like Boltzmann-Gibbs, Tsallis, or other form, and we use the relation with P and theta, and you replace in this equation. And now we have a function, and using this function, we inverse the function and put here, and I obtain the entropy. It's a simple protocol, and now I will show two examples. The first the Boltzmann-Gibbs. The Boltzmann-Gibbs, we remember of a ground state of a two-level system. You have this expression, and follow the protocol, we invest these functions, we obtain this relation here, and in sequence, we put in the equations, the Clausius equation here, and you obtain, of course, the Boltzmann-Gibbs entropy. Now, finally, we need to find the functions that I put in my Hamiltonian to obtain the same situations in the quantum model. And I put here, I think that's okay. Here, and I found this expression for the interactions, the quantum interactions. The quantum interaction to obtain the Boltzmann-Gibbs entropy and to obtain the expression, the thermal statistics of Boltzmann-Gibbs using a simple problem of quantum to level, of course. Now, here, the second application is Tsallis Q thermostatistics. Of course, you know that is the equilibrium probability, and following the same protocol, it's direct to obtain the Tsallis entropy. It's direct to obtain the Tsallis entropy, and of course, it's necessary to see that we found this expression for the interactions function in my quantum problem. Oh, we have now a protocol that we can obtain every entropy using a quantum problem, but the question, of course, here. Here is we present the Boltzmann-Gibbs, the Q statistic for two Q. And the red curve is the Sousa-Noble thermostatistic that we're using theta, lambda is equal to theta, okay? And here is the difference. Here is the probability of found the particle in the ground state as a function of the effective temperature. Effective temperature is, of course, it's here the entropy, the four entropies. And in sequence, we present the interactions, the quantum interaction to obtain the quantum, the statistics, the different statistics. Here's the interactions. Here. No, that's not a problem. Oops. Here. Okay. The black, it's Boltzmann-Gibbs, blue, Tsallis, red, Tsallis, and red is here together with the black. But if here I put the inset where I use only the small temperature. Here is you can see the difference situations of the interactions, quantum interactions. Okay. To conclude, different thermostatistics can be extracted from a two-level quantum system. The protocol is based on the two-level Hamiltonian, in which the non-diagonal term is associated with an effective temperature. And we use a non-diagonal to associate to effective temperature using the protocol, and the functions form of this term defines the functional form of his conjugate parameter. That is the entropy. Consistent with the thermodynamic framework, the present approach establishes heat work-like quantities from the thermodynamic first law, similar results to the second and third laws of thermodynamics, is that the efficiency of the proposed Carnot cycles is independent of the thermostatistics. I think that's Evaldo proved this case of the cycle, the Carnot cycle. Okay, and finally, I can say that I have a very happy life. My life is a very happy life, and part of this happiness was made possible by Mr. Tsallis, and as a consequence, many of you here. Okay, thank you, everybody. Thank you, Tsallis.
Thank you, Andre. Questions, please? Evaldo?
Okay, Andre, thank you. With respect to the Carnot cycle, you can perform an experiment in two-level systems.
Yes.
Why not propose this some?
Yes,
Yeah.
that's good. The question is I think that's I like these results, the simple results, and we can propose experimental using, for example, if you know that's the okay. Here, it's a Pauli operator of the X spin. Like he is like a Q bit. I think that's the lambda or the F theta is like you can use a magnetic field. A magnetic field, not constant, but a magnetic field, and here in this using X directions. Okay, and here the diagonal term, it's a normal spin, the quantum spin, the I directions. I think this. Okay, it's I am working with this paper. It's not. Yes, I don't know. It's only a idea. But I would like that you can help me because I don't. It's not close. It's a paper that's not close.
Hi, Andre. And this is exactly this point. Constantino asked you a question. Why you consider two variables, lambda and z, here, and as for us it would be most likely they were the same play the same role in the development. Then you separate them, okay? But even you get always the product lambda times z appears, and so the physical interpretation becomes a little bit tricky. If you could discuss a little bit.
Yes, possible. I don't. Now I have not an answer for you.
In the problems where there is overdumping, that you also worked, and
Yes,
Evaldo,
yes,
Fernando, and Suarez from Será.
Yes.
It appears two temperatures. One, which is the normal kinetic temperature,
Yes.
and one which is a sort of effective temperature. That situation with two temperatures, can you transform it into a three-state quantum problem?
It's a good question. It's possible. I don't know, but it's possible.
You don't see it,
No, no.
but maybe.
Yes, yes. I think that's a good propose for me because it's easy. Three level is easy to solve. Yes, yes.
And the
expression
of the genre
structure, yes, yes.
you would have minus one temperature and its entropy minus the other temperature and its entropy. Something like that.
The next paper for of us.
Okay. Any other questions? If not, well, let's thank all of us. And now coffee break. Yes. Let's start. Let's start. Okay, I think we can start again after the coffee break. And they told me that there is a folder posted in the web page that where you can put some photos, something, and you can take out also photos, as far as I understand, right? So if you have any photos, please put them inside that folder and you can download from the folder, whatever, okay? The folder is, the link is posted on the web page of the conference.
Okay.
Right? So let's start this session with Cassio Amador. And please, Cassio.
Okay, good morning. Can you hear me? All right. Right. First of all, I would like to thank you for this opportunity. Thank you, the organizers. And it's a great pleasure for me to be here in this special event for Tsallis' birthday. My name is Cassio. I am a physics professor at this university here, the Federal University of Technology from the state of Paraná. And I hope to show you how what I did to find the best value for Q to retrieve more information from a system if the system have discrete values, and if this works or not. So just a little introduction. I'm not an anthropocist, okay? My main research is in plasma physics and data analysis. And also I'm from a region in the Paraná states, in the north region of the state. Here we are in Rio de Janeiro, and I am from Londrina. The main economic activities are services, livestock, and agriculture. And actually, the main cities in that region started because of coffee plantations. Why I am talking about this? And also, we have lots of universities and a lot of research going on various topics. Let's talk a little bit about coffee, okay? There's a lot of research to improve coffee production and processing of coffee. For example, we have a technology that it's called freeze-drying coffee. In Portuguese, it's liofilização. It's a process to make instant coffee that it's much better than regular instant coffee. It involves freezing until minus 40 degrees Celsius and sublimating the water directly from ice to gas state. So you have a much better taste for the coffee. And this process is done in my city, in Londrina. For example, we have this, it's a commercial brand you can find in some supermarkets. I don't know if Tsallis already know this brand. So I brought here as a gift for him. Okay, we can have one? Nada. And also, I brought another one if you want to like open in this afternoon in the coffee break for other people to taste. You just need hot water, okay? So you have to. Okay. So this is one of the technologies that we work with coffee. Oh, I forgot to tell this. Of course, this word liofilização came from the Greek, as a lot of words. And this technology to produce the instant coffee, it's not the only technology that we work on. We also work how to improve the coffee grain itself. And one of the ways that we do that is using entropy. Okay. Let's talk a little bit about bioinformatics. Bioinformatics works with data processing and analysis from biological systems. For example, we have a lot of research on how to improve the DNA of coffee and its genomic expressions. How can we improve coffee to use less artificial chemical compounds? How do we improve the coffee to have a better taste or to deal with extreme temperatures? So near Londrina at UTFPR CP, where I am a professor, there is a small but strong group of bioinformatics. So I told you that I work in plasma physics, right? And then I took a second master's degree in bioinformatics there with this group because I really like the subject. What is this genomic regulation? Here I brought an example from brain cells from rats. Here we have a young rat sample. And here we have a list of proteins that can be expressed or not on these brain cells. The green ones are least expressed and the red ones are more expressed than the average of genes, right? If you compare this with old rat brain cells, it's very different picture. So we can measure genomic expressions. To analyze this, one way that we can do is to change these colors to numbers, to float numbers, right? So here, it's an example of a table. This is the gene numbers. And each line here, it's a different time. So for example, the first line, you take a sample from the cell and you put in the machine, and the machine will give a result, something like this. Then you have the first line here. You wait some minutes, for example, and you take another sample, and you have the second line. Then you wait more minutes, and you take another sample, and so on and so on. Each test can cost around $100 to $500 each line here that you see in this table. So it is expensive to have these data points. So one question is how to infer this genomic network, this network between, when I say network, it's because each protein can interact with other proteins. One protein or two proteins can, for example, enable the production of one protein or can disable this production. For example, this is one model. Let's suppose we have in step 1, we can see the protein G1. In step 2, we can see G1 and G4, and G3, it's not so expressed. Let's suppose in step 7, we have something like this. And we can see that the idea is how, with just this information from the steps, you can find this network. It's a very hard question to answer. There is a lot of methods to do this. The first thing is that we assume that there is an order in the system. The system is ordered. And to infer this order means to find out which structure exists underlying these expressions. One problem that we have in bioinformatics is that we have thousands of connected genes and just a handful of measured time steps. For example, you can have the measurement of 5,000 genes and you have 10 time steps. Then I give this to you and you have to find the correlation between all these 5,000 genes with just 10 time steps. And this is a big sample, okay? You can have even smaller samples. So information is very scarce and every bit of it is valuable. And also, already given a hint of what we can use, there is definitely a long-range interaction at play here. One way to find this network, I will skip some details, but it's to use this criterion function that utilizes this HQ function. And this HQ function actually have a conditional entropy here, written like this. So how can we guess the structure using entropy? By brute force, we test all possible combinations, and we measure the entropy for each one of these combinations, and we try to find the one with the least value for this criterion function. So actually, we are checking the least values of the entropy, of the Q entropy.
For a fixed value of Q.
Yes, that's it.
But up to now it's arbitrary.
Yes, I'll get there. So to use this method, there are other methods. For example, nowadays are machine learning methods and so on. But to use entropy, we need to use discrete values because I need discrete values to put in this formula. So that table with float numbers, we change to discrete values. We don't have, so for example, you can define that the least expressed is 0 and the most expressed is 1, or you can use 3 numbers. For example, here I'm calling the number of discrete possible values as W, okay? We can use 3 numbers, so 0, 1, minus 1, 0, and 1, and so on. I will talk to you about some previous work done in this. This guy, Fabrício Lopes, during his PhD thesis at Unicamp, attended a seminar from Tsallis around 2008. And he's not a physicist, but he tried to apply this Tsallis entropy within this inference method for gene networks. No one had done that before. So he was the guy that did this. That equation that I showed you before, it was his work in his PhD. And he found out, surprisingly, that the results were much better compared with the Boltzmann-Gibbs entropy. So here is one of his results from his PhD. This is similarity. Similarity, it's one way to measure if the network that you are inferring, the structure that you are inferring, is close or not to the real network that you are expecting. And here, oh, it is Erdos, Reni, and Barabasi Albert. He tried a lot of different scale, I'll not enter in these details, but he tried like 4 different scales in his work. And here, answering your question, by brute force, he tests this for a lot of values of Q. So for each one of these, he needs to evaluate everything again for each value. And he had no idea which value was the best one. He found out that the best one was around here. So you can see more points, because he was trying to find the best value of Q. And he found out that for when he used binary discrete values, he found out the best Q is 2.5, okay? Best, okay. You can, for example, you have some biological systems that are already very studied. So you have the network, you have a very complete network, okay? Then you compare the measured values, you try to infer the network, and you compare with the expected network. This is one way. The other way is to simulate. You simulate the network, then you have total control of the network. And you measure this network as if you don't know the structure of the network. Then you try to compare the results that you have from the inference, from the inferred network to the simulated first network.
Networks are large dimensions. Finding something a little bit different because of chaos, so probably they will be working on the chaos. So there's any control tests and so on.
Yes, there's a lot of tests. Yeah, like there's a lot of people working on this and trying to infer gene networks, but they used Boltzmann entropy. So there was a lot of methods and tools to work with Boltzmann entropy.
Then probably the best one is something like one.
Yeah, it's around here. Okay.
How do you know? I mean, so this is the best. Should be something to check it out. So that's why I asked that. So
Okay. No, but okay. So, all right, and his PhD won best thesis of the year at Unicamp in the informatics department, in the computational department. He also tried with W equal 3, and he found out it's around. He found out it's around 1.5 the value of Q if you have W equal 3. Intriguing. So he achieved these results, and 10 years later, now he's supervising a physicist, me, okay? And that numbers bugged him for all these years. He was trying to answer why these values. So my mission was this, to answer this question, why? Why Q 2.5? And is it possible to arrive at this value from the dynamics itself, from the gene network dynamics? I tried some possibilities and arrived at a lot of dead ends. So some hypotheses, for example, the additivity. Does it play a role here? So for example, because of the structure, the network structure, the way that you sum these parts of the network can influence the large result. The complexity of this in activation between genes. So we can model, for example, as logical parts, if it is an and, or, nor, sure, and so on. The network topology itself plays a role here. There is an influence of the predictor genes and hub genes. You have genes that have a connection with a lot of other genes. You have genes that are very isolated. What can we do? More than 1 year of testing had passed. And to be honest, I almost gave up. I almost gave up because nothing that I tried worked. What it means that it didn't work? It's because everything that I tried to change in the system gave the same result. I tried to change the scale, change a lot of parameters, and it gave the same result. And then I find out that the possible explanation have nothing to do with gene networks. And I still remember the day that I arrived the possible solution. There was the famous click in my head. There was a click that everything made sense, and I will try to show you what I did. And it is so basic that actually I spent months looking for if anyone have done this research before, and I couldn't find. If some of you already have seen something like this, please tell me. I tried to look for this. Okay, we have this expression that all of you know so well, so much better than me. And when you plot, this is entropy by the probability. One of the probabilities, it goes from 0 to 1, and we have. Oh, sorry. Okay, sorry. Oh, that's a big mistake. Sorry. So I plot for different values of Q. And okay, why I did this? Because I wanted to check something. And can you see something different here in these curves? Okay, it's a lot of curves, but especially here, I saw something different. The slope changes. The slope changes between this value in this region. You have here a type of slope, and here it's a different type. What I mean by slope, to be clear in the following slides. So we have here, okay, it's around this value. Then going back to basics, what it means to retrieve more information. If you have total disorder or lack of information, we have maximum entropy. So if I want to retrieve maximum information from a small quantity of data, I need to have an entropy that gives the most difference in entropy based on very little information. So the curve with the steepest slope should give more entropy variation in exchange for a small quantity of information. And so I proposed this, I called relative entropy. I just divide the entropy by the maximum entropy. That's it. If we use the Tsallis entropy, the expression goes like this. Remembering W, it's the number of possible discrete values. And the case of Q going to 1, it is like this. Then to find the best value, we took the one with the greatest concavity, or the greatest slope, as I called. I just, I divide by, I make a derivative by Q, n equals to 0, okay? Which results in this equation. So with this equation, we can, for a given probability distribution, it is possible to numerically find the value of this Q minimum that maximizes the amount of information that can be inferred from the system. And it is, it's not a good equation to work by hand, but you can solve it numerically. So let's see for the case W greater than 2. So what I did here, I generate a lot of random data for different W possible states, and I try to find the minimum value of Q. So I have a lot of random data, and I have this value of Q, and I made an average of the value of Q, and that's what you are seeing plotted here. So for example, this average for W equal 3, it's 1.52, for 4, it's this one, and so on. But actually, I still don't like this one. This one for me, it's strange. I think it's, I tried a large data set. I generated a really large data set, but I still think it could be improved, this part. But this part, it's, I think it's okay. And the more interesting case, it's exactly for W equal 2. Because for W equal 2, we have only 2 probabilities. We have the probability of being 0 or 1. Then the equation goes like this. And we have 2 extreme cases. If one of the probabilities is 0, it diverges. And so the case Q equal 1, it's the only numerically possible. And if the probabilities are 50%, the above equation goes to 0. Everything goes to 0. So yeah, we have maximum entropy. When we solve numerically between 0 and 50%, we have this plot here. And it's surprisingly a smooth curve. So here we have the probability from 0 to 50%, and here we have the minimum value of the Q for to minimize that equation. Here, when it goes to near 50%, it diverges. The meaningful values are between 2.42 and 2.47. And the average, weighted average between these values, it's 2.46. In summary, comparing, this is another plot from Fabrizio's work. He found out Q equal 2.5, and I found out that actually it is 2.46, exactly 2.46, or sorry, not exactly, but it is between 2.42 and 2.47. So if you have a lot of probabilities between this, between 0 and 50%, average it will go around this value. So that's why he found out 2.5. So he found out 2.5 not because of the gene network or anything like that. It was just because you have a system that is discretized in binary states. Okay. And when we compare with what he found out for W equal 3, he found out 1.5, and in average, I found out Q 1.52. Final remarks, these results are still unpublished. So actually, you are the first one that are seeing this outside of the bioinformatics group in my city. I think the results for W equal 2 are okay, very good. But for W greater than 3, it needs to be improved. And research is still ongoing to apply to other information systems. For example, digital transmission signal sources, right? So thank you for your attention. Here's my email, and happy birthday, Tsallis. And here we have the 3 pictures. The first one, 2003, I attended a seminar that you gave in Londrina, in Paraná. In 2008, you connected with Fabrizio. 2020, Fabrizio shared the information with me, and today I'm sharing the results to you. So is this a long-range interaction? Maybe. Okay, thank you.
Thank you. Questions, please?
I am happy because if no one raised his hand, and oh, but this is obvious. I already did this. So for me, it's okay. Let's go.
I understood your work very well, actually, so it's very cool. But I couldn't understand your question about slopes. So you said, so if someone knows, maybe tell me and so on. What was it? Can you repeat your question? Then maybe someone really helps you.
The question.
You said, so you see some changes in the slopes and so on. So I missed
okay,
it.
okay, sorry. Yeah, it's because
I couldn't get what was your question, and then what you are really wondering.
Okay. It's because of the time. I difficult to explain. Okay, this one. So yeah, my question is, for example, you have a system with very few data points. So you want that any data point that you have can give you more information. Okay. Yeah, but the question is, if you have, for example, let's suppose that we are here at this one, the lowest one here from Q equal 8, right? When you have no information about nothing, you have maximum entropy, because everything it's possible, right? So we are here at the middle one. When I give you some information, then you can start to change your probability to another value. When you change this probability, if this slope, if it's too flat, this new probability, you can't see a change in entropy. You can't see this change in entropy. Let's suppose you go from 50% to 40%. If you are here in Q equal 8, and what you're measuring is entropy, you don't see the probability. You are seeing the entropy. So if you are here and you go to 40%, for example, you will not see so much change in entropy than, for example, here, and this one, which is around 2. Here, if you are in 50% and then you go to 40%, you see a larger difference in entropy. Then if you go to this one, as you go to smaller values of Q, let's see here, for example, it also have not so much difference in entropy, and it goes to 0 too quickly. So it's not so good to measure information with that entropy. Because what we want to know is, any information that I gave to you, does it change entropy in a measurable way or not? It's another way to make the question.
I think straightforward, right? So this is n to 1 over 1 minus gamma, and then if gamma is basically larger than 3, then of course, so the system will not diverge quickly. If it's not, then it will. So I believe this is the case.
Yeah.
So if you make an estimate wrong, for instance, your exponent is something 2.9, and then you made an estimate, mistake in the estimation, root 3 something, just a tiny bit, will make more than 500% mistake for it.
Yeah, but in this case, the information is in the specific case of gene networks, the information is so sparse that if you go to 2.8 to 3 to Q equal 3, it's not a big problem actually. It's not so different.
So 3 is really pretty close. So if you
okay, Q equal 3, it's a different, yeah.
Number 3 is very
okay, yeah. I understand that.
Okay. Any more questions? Okay. If not, let's thank you again. Okay, and the last talk for this session by Sergio. Yes, you use this slide. No? Yeah, okay. De cima é o laser. Para passar, é com isso aqui. Tudo para outro lado. Como que é? Não. Acho melhor. Como que é? Onde é que você aperta? Mais para trás. Esse volta. Ah, com isso. A seta para trás. A seta para frente. Aí esse aqui eu ponho. Só vai pressionando. Tá bom. Segura. Tá? Ok. Okay, good morning, everybody. I want to thank first the organizers for giving me the opportunity to talk here and also for the support to come here. Second, I want to say a few words about my relationship with Constantino. And I also will talk
on behalf of my dear friend and colleague, Pancho. So we came here in the 80s, in the middle of the 80s, to Constantino group in the CBPF, who did our PhDs. And then we started with a PhD. Constantino was my advisor. Evaldo was Pancho's advisor. And then we really had a good time here. This was wonderful. This was always a wonderful group with plenty of wonderful people. So you made us always feel at home. We learned a lot. We made a lot of very good friends. Many of them are here today in this room and or were previous days. So we really enjoyed our time here. And perhaps, as Hugo said, the most important thing we learned from Constantino, from the group, was to enjoy doing science. Then we came back to our city, to our university in Cordoba, but Pancho came a couple of years later because he stayed here to do a postdoc. But by the end, we both went back there. But we continued our interaction with Constantino and with the group for many years. And during all this time, Constantino supported us in many, many ways, different ways, and helped us to develop our own statistical mechanics research group in Cordoba. So thank you very much for everything. Now, among the many things I learned with Constantino, I learned about critical phenomena, and I continue until today working in these and related topics. And so now I will speak about some particular critical phenomenon that appears in cellular biology. Let me first mention the collaborators. The head of this project is Ante Chialvo, many of you already know. Orlando Bilone is a guy from our group in Cordoba. And last but not least, the Zamponi brothers, Nahuel and Emiliano. These are two biologists, young biologists, very skilled experimentalists who did the experiment I will show you now. So the talk is about mitochondria. Mitochondria are a set of tubular-shaped organelles that can be found inside every cell in most eukaryotic organisms. And its main function is to produce ATP, which is a very important molecule since it participates in most metabolic processes in the cell, providing energy to the chemical reactions. So we may say that the mitochondria are the power supply of the cell. There are different hypotheses about the origin of mitochondria, but the most widely accepted one nowadays is the so-called endosymbiotic theory, according to which mitochondria were originally primitive prokaryotic cells, that is bacteria that were incorporated into one of the primitive eukaryotic cells about 2.3 billion years ago. Then symbiotic relationship was established between these two organisms in which mitochondria receives nutrients, food, and in return, they provided a lot of ATP to the cell. Now, mitochondria is not the only mechanism the cell has to produce ATP to gain energy, but it is by far the most efficient one. So it is believed that this incorporation was crucial to the development of multicellular organisms, because it was thanks to this, those cells had enough energy at their disposal to develop through evolution multicellular organisms. Now, along the time, all this time, this relationship became more and more complex. And nowadays, mitochondria not only produce ATP, but they participate in many, many very important cellular processes, so that nowadays mitochondria are crucial to cells' life, in the sense that if something goes wrong with mitochondria, the cells get sick and eventually dies. Now, the organelles in the mitochondria interact among them, and they form a network. As you can see in this is a real image taken from a real cell, where the mitochondria is a yellow part, and the, blue part corresponds to the nucleus of the cell. there are between 1,000 and 100,000 of these organelles in the mitochondria, depending on the type of cell, the type of organism, etc. Now, this network is not static, it is dynamic, it evolves all the time. It is evolving inside us in every one of our cells. So all the time there are clusters are formed and broken all the time, but the whole process is stationary. Now, this dynamics is based on two basic microscopic mechanisms called fission and fusion that were proposed among 12 years ago, very recently, through this model by these people here. And according to this, in this model, they represented mitochondria as dimers. So the dimers interact through the tip. According to the proposal of these people, there are only two types of mechanisms here. So they can fission or fusion the tips through these basic processes here, tip to tip or tip to size. Now another one. So, okay. So if we think that the tips of these organelles, of the dimers, are the nodes of the network, these nodes can only have a degree 1, 2, or 3. There is a minimum degree because they are attached always to a dimer, and there is a maximum degree according to this proposed mechanism. So the whole process can be thought as a set of chemical reactions between three species, nodes of of degree 1, 2, or 3. Okay, so for example, the tip-to-tip, process is thought as a chemical reaction in which two nodes of degree 1 are merged to form a single node of degree 2. Of course, there is an inverse process and something similar for the tip-to-side process. Now, this is a mean field model. Okay, here there is no space. Every dimer can interact to any other dimer. Then the whole process, dynamic process, can be simulated using, oh, sorry, I forgot. If we think this as a set of these 4 chemical reactions, there are 4 rates that are considered constant in the model. But from some arguments and some rescaling, it can be seen that there are only 2 independent parameters in the model, which are C1 and C2, the rates of fusion in the tip-to-tip and tip-to-side processes, normalized by some common one of the 2 fission rates. So the whole process can be simulated using Gillespie algorithm. It's a common, very used algorithm for chemical reactions, where we are keeping constant the number of dimers. Okay, this is a process, a network that evolves where the number of nodes is not constant. What is constant is the number of bonds. Then these people, this model was validated in this paper and many other ones by comparing simulation results with empirical ones. And there was one that called particularly our attention. This was this one. They analyzed the cluster statistics using this simulation process. And they found that the side fraction, the largest cluster, follows this blue curve here, and also this average number of dimers per cluster have this peak here. And this is characteristic of a percolation phenomenon. Okay, so they conjecture, they made a hypothesis that maybe mitochondria lives in a critical state. And here is where our work starts. Our first objective was to check this criticality hypothesis from these people. So the first thing we did was to calculate the complete phase diagram of the model by varying the 2 parameters of the model. And we did that by following the peak in this, in the susceptibility, that is the average cluster size, this usual susceptibility for percolation. So we draw this phase diagram, and you can see here, between a percolated phase and a disordered phase. So now the question is, well, first of all, this phase diagram was calculated for a fixed size, fixed number of dimers, 15,000, because it's the average number of dimers of organelles in the cells we analyzed in the experiments. But I have to mention that there is some size dependence in this phase diagram, but it is relatively very small, this is dependency for the range of values of sizes for real mitochondria. So the question is, in which part of this diagram can we find the real mitochondria? To answer this, the biologists perform a series of experiments that consisted into taking images using confocal microscopy on genetically modified cells, such that the cells express some protein, a fluorescent protein that gets attached to the mitochondria. So when you illuminate the cell with light of some particular wavelength, mitochondria brags, and you can take an image. And we have an example here of one of the images where the mitochondria correspond to the green part of the image. The cells they used were mouse embryonic fibroblasts, and these are epithelial cells of the embryo. And the reason for this choice was that these are extremely flat cells. So they are almost quasi two-dimensional, and then they avoided the difficulties of analyzing a three-dimensional structure. Then from these images, we had to extract networks, and this is not an easy task. We developed a procedure using standard image processing software. We didn't invent this software, we just applied them. That is a pipeline that consists basically of two steps. The first one is to binarize the image. That is, the real images, the colors here are artificial. The real images that come from the microscope are grayscaled. So you have to first to transform these grayscaled images into black and white images. This is the binarization part of the procedure. And then this processing of the image from which you extract the network that is called a skeleton. Now, this process is plenty of artifacts. It's not easy to extract a network from something like this. So we devoted a large part of the work to calibrate the method and to get reliable images. I will not enter into details because it's very technical and boring, but the main source of problem here is the fact that the binarization involves the usage of a threshold. That is, you have to put a threshold to decide whether a pixel is black or white. So we introduce an arbitrary parameter into the processing. So we calibrate the procedures to find a reliable interval of values for the threshold where the networks to be extracted do not depend too much on the choice of the threshold. And here is an example, a first example of calculation. You can see here the probability distribution for the mass size of the clusters. The mass is defined just as the number of pixels in each cluster. You can see that it follows a power law decay. This is for the same image for 3 different choices of the threshold. And in all cases, we observe the same power law, so it's rather robust. And this was the first evidence of criticality. To get a more deeper evidence of criticality, what we did was to perturb the state of that network, trying to move away the network from this supposedly critical state. And to that, we took different groups of cells and submitted them to a treatment with substances that promoted either fission or fusion. For fission, we used paraquat, which is a poison. Paraquat is a commercial herbicide, very used all around the world, very, very common. And the crazy thing is this herbicide not only kills weeds, only kills animals, including us. And it's very, very dangerous. However, it is one of the most widely used all around the world in agriculture. Anyway, the effect of paraquat is precisely at the level of mitochondria. It breaks the mitochondrial network. You can see that in this example here. this is a normal, this is a control group, this is a normal network, and you can see in the paraquat treated a much more larger number of very small clusters than in the normal case. On the other hand, to promote fusion, we use mitofusin. Mitofusin is not a poison, it's a protein that is already present in the cell, and it forms part of the process of fusion normally. It promotes the fusion normally. So the treatment consisted in to manipulate again the cells so they overexpress this protein. They produce a larger number of this substance. And you can see the effect is very clear here in this image here. All the mitochondrial network almost collapsed. And we have a few very large clusters and a very small quantity of small clusters. So we have these three groups of cells, and with this we try to parameterize the model. So to locate this real system in that phase diagram we already have. And to do that, we calculated two things. We calculated many things, but I choose two things, two quantities that are the average degree of the network, that has to be between 1 and 3, obviously, and the order parameter, that is the size of sites in the largest cluster in the network, as a function of one of the two parameters, keeping the other constant. We have curves, segmodal curves like this, then we change this other parameter, we have another set of curves, and we generated a family of curves from which we draw this parametric plot of the order parameter versus the average degree of the network. And what we observe is that except for one point, a common crossing of all the curves, for any other point, we have a unique point corresponds to a unique choice of the parameter C1, C2 of the model. So we use this to parameterize the model. That is, we took the three groups of cells, the treated cells with paraquat, mitofusin, and the control group. We calculated those quantities, we averaged them inside each group, and then we plot in these graphs here, and these are these 3 points. From this, we extracted the values of C1, C2, the parameters of the model, and we draw that on the phase diagram, and voila. That is, the normal state lies almost around the critical line, while applying each one of the mechanisms drive the system towards the percolated phase, in the case of mitofusin, or into the paraquat, disordered phase in the case of paraquat. Something I didn't mention, I forgot, is that in the case of the treated cells, they all die. Always. After a few hours, all the cells that were treated died. That is, any departure from the normal state leads to a pathological state and invariably to death. Okay, so this was the main result of this first work. That is, the healthy state lies around the critical line, while any departure leads to a pathological state. Then this raises new questions, because we are defining critical here as the point with maximum susceptibility, but this is a finite system. So do this fission-fusion mechanism really generate criticality? That is, we are asking what happens if we increase the system size, we change the system size. Do this system follow the expected scaling, finite scaling relationship? If so, if it is indeed a critical situation, which is a universality class, and finally, what happens in finite dimension? Because all the conclusions were obtained with a mean field model, but the cells are real mitochondria finite, and in particular, the cells we use are almost two-dimensional. So to answer that, how the time? Right. The first thing we did was to perform the standard finite size scaling analysis in the mean field model. So we calculated the susceptibility, that is the average size, average cluster size, and then we found a divergent peak that increases with the power law, so we can extract. There is something wrong there, but okay. We can extract the critical exponent from this. We also follow the size of the second largest cluster that also show divergent peak, and from this we could extract another different critical exponent. We analyzed the cluster distribution function that is expected to show a power law followed by a cutoff, a size-dependent cutoff that also increases with the power law. From this, we extracted this, these critical exponents, and then comparing with the whole library of critical exponents in the literature, we found for tau, that is the critical exponent of this power law here, and for the fractal dimension, which is the power law of the second largest cluster, or from the critical exponent of the cutoff, we find a quite good agreement with the mean field standard percolation critical values. In the case of the susceptibility, the gamma, we found something very disturbing, that this exponent is almost twice the expected critical exponent for mean field standard percolation. But then we realized that there is some unusual, some anomaly here in this scaling here, some finite size effects that is, okay. We also find this is due to the fact that there is a lower cutoff also here that is size dependent. Usually this lower cutoff do not depend on size, but here it does depend. Anyway, a detailed analysis of this shows that this strange effect that creates this discrepancy disappears for very large system sizes, much more larger than the real mitochondria, but it doesn't matter because we wanted to look at the universality class. So we can conclude roughly that this system is in the class of mean field standard percolation. This is interesting because it's not obvious. We could expect here directed percolation, universality class. Then we went to see what happened at finite dimension. We introduced another model, a very artificial model, a toy model that incorporates some simple rule that is, I think, it's not very important. A simple rule for generating bonds and killing bonds here with some probabilities in such a way that we can see that this leads to those basic mechanisms of tip to tip and tip to size. These are only allowed here. And we generate structures from this type where we have nodes with degree 1, 2, or 3 in a square lattice. And that's it. We didn't want to see nothing realistic here. Then we performed the whole analysis standard. We found percolation. Then we performed the finite size scaling analysis. And then, well, we obtained a clear evidence of 2D standard percolation universality class. And here there is no anomaly at all. So this was a problem of the mean field model. Finally, we looked at the real system. So our colleagues performed a new set of experiments. This time, this happened 2 years later. They had more experience, better technologies, better equipment, so they could analyze. The previous one, where we analyzed 15 images. Here we analyzed 100 images, and with much more better resolution. We observed clearly the power laws expected in the 3 quantities. And from this, we extracted critical exponents. And then we compare with different universality classes. Here simply is to show that here there is the critical exponent for mean field, for 2D, for 3D, for standard percolation, directed percolation. And after a comparison of all these critical exponents, one can see that the experimental critical exponent coincide, the better coincidence is with those corresponding to the 2D standard percolation. So in conclusion, first of all, the fission-fusion balance, we show that this dynamic puts the mitochondria into a percolation-like critical point. We have several evidence of that. Second, that any departure from the critical state leads to a pathological state. The healthy state is the critical one. And finally, the mitochondrial critical point belongs to the standard percolation universality class. So these are the papers, if anyone is interested. So thank you very much for your attention and happy birthday.
Hello? Can you go back to that expression that you had for the correlation function? A power law times an exponential, that one. No, no, that one, yeah. Have you checked with experiment or simulation that expression, or you just suppose it is correct because it's the usual one?
That's it. We suppose it is correct because it's the usual one, and from this we have the definition of this critical exponent that you can compare with other models in the literature.
Okay.
But,
so you did not really check some of those
no,
expressions?
No, not at all.
Okay.
Regarding your experiments in comparison to the model, you concluded that the best model would be the 2D percolation, right?
Yeah.
This would apply also for other cells. This is because you have your very flat.
I think so. We don't know, but I think so. I think that if you take another type of cell with more three-dimensional, you will see standard percolation three-dimensional critical exponent. Yes, that's it. Because we have two models and the experiments, and when you always see standard percolation, but the dimension. No.
Yes. No, but then it's not.
Sergio, the dynamics of the system remind me of self-organized criticality. Yes. So do you think it is possible to perturb the dynamics in order that the system leaves the critical state, but does not die, in the sense not poisoning it, but leading to a state that maybe it can tune again spontaneously to the critical point?
Yes.
So is it possible to perturb the mitochondria network dynamically, in the sense that it goes away, but not so far away that it can come back, like in a self-organized criticality system?
Yeah, well, this was the idea of the experiments. We moved the real mitochondria, driving it away from the supposedly critical point using those drugs. In the models, we didn't try, but I think it is perfectly possible. Yes, to modify the dynamics, so you drive it away from the self-driven critical point.
You can propose that to the Zamponis brothers,
yes,
because it would be nice to check it experimentally.
Well, actually, this was is one of the projects. This was a future project, but it was stopped by several ways because this network actually, I think that the mitochondria, the organelles, are not diffusing on the cell. They move over the cytoskeleton. Okay, so this is somehow active matter problem. The mitochondria, once they leave, when you have a fission event, one of these organelles moves and links to another one that could be very far away. So it's very interesting to analyze and to perform experiment analyzing the dynamics of the problem. And now, the first experiment did not allow to take movies because when you take a movie, you lose, for technical reason, I don't know, you lose spatial resolution. In the last experiment, they improved their solution, and they have movies, so you can analyze dynamic too. And this is one of the ideas is to do precisely that.
Thank you.
More questions? Okay. If not, then we can thank all the speakers of this session.
primeiro eu quero dizer que mais de uma... I speak in English. More than a year ago, I had a dream, and I'm not lying, of coming to this event. Then I sent, because I knew Constantino was going to turn 80, I came to the 60th birthday. I could not come to the 7th, so I was waiting anxiously for this party, and I had a dream. So I sent an email to him. Say, Constantino, are you going to, is there going to be any party? And a few days later, he said, yes, Fernando and Evaldo are organized something. He gave the dates. I blocked at that time. Many months ago, I bought my plane ticket. I made the hotel reservation. And about a month ago, I prepared my suitcase. I am not lying. I am not, yeah, because I wanted so much. By the way, for the ones that don't know, I did my PhD, with Constantino in the 80s. And I remember one day I was standing in front of his office by chance, and he came very euphoric from that famous plane trip from Alagoas. And the first person he met at, it was me. And he said, I just realized the statistic of Boltzmann Gibbs on the plane. And for his excitement, there are moments that we memorize that scene, right? Where exactly how that person spoke to you. And I memorized, I have in my memory clear. At that time, I knew that was something important because of his excitement. But of course, I had no idea of what would become in the future, right? So, yeah, so I have such a big privilege of working with him. But so the first speaker is Kurilev, and please, I don't know how to operate this, but we can get some help.
You see? Okay. Más no tem problema, não?
Para mostrar.
Ok. No, no problem. Okay. Okay. Thank you very much for attending this talk. I'd like this time to emphasize some problems related to some nonlinear diffusion reaction equations like Fisher-Kolmogorov equation, but applied to complex system. We are introducing as well some result and application to complex system, such as macroeconomic system, that is a good work that we are developing now. This work, this talk, is framed in the nonlinear differential equation of statistical physics. Some of the problems that we are emphasizing here are advanced with my student, Eduardo La Rosa and Nicolas Angel. Well, in the line of this talk, I would like to speak about my history with Constantino.
I'd like to summarize my record with Constantino. In 1993, I met him in a period of 4 years. He was my PhD advisor. After this, I returned to my country, Chile. In 2002, the Bachelor in Physics was created at UCN, and Constantino visited us, visited the first generation of students in Antofagasta, developing some stimulating discussion and talk with him, with all these students. In 2004, he visited the SOCHIFI, Chilean Physics Society. But I would like to remark a meeting in Este when we had some interesting conversations about some social topic related to the social situation in Chile. And he asked me, "Oh, Sergio, what about retirement in Chile?" And I give you an answer that Constantino was horrified and scandalized with my response because was my opinion. Do you remember, Constantino? Someone was participating in the conversation. I don't remember. Marisa. Okay. Nesta, no? Okay. But this time, I would like to make a reminiscence of such conversation, and I try to give an answer not based in my opinion, but based in the Fisher-Kolmogorov equation. Okay. But Constantino is influencing the development in physics and the statistical physics in my institution, because in different situation he is present there. In 2019, yes, we organized the first workshop on statistical physics with our student, with our group, with our postdoc and collaborators in general. When the creative team told me about the proceeding book, they created this cover book, and the creative team told me, "Oh, Professor Sergio, we believe that there are two superheroes in statistical physics today. Who are they?" And they showed me this cover book. James and Tsallis told me, and they told me, "What about your opinion?" "Oh yes, I think so." You can print it here. Okay. After this, in 2021, we celebrate the second international workshop on statistical physics, and the actual product was some publication in several magazines. I participated the celebration in 1993, 2003, 2013, 2023. I like to participate in many other celebration of birthday of Constantino. Y esto me gustaría decirlo en castellano porque es más fácil decirlo para mí. En chileno, en español chileno no hay problema, Antonio. No. De que realmente ha sido una tremenda persona, digamos, apoyando la investigación. Directa o indirectamente, en Antofagasta ha sido de una tremenda influencia, pero una influencia positiva. Mis estudiantes están aquí, yo a ellos les he contado las cosas que me enseñaste cuando yo era tu estudiante. Así que bueno, por eso quiero decir estas palabras, digamos, porque me es más fácil decirlo en castellano. Más también quiero participar de este reconocimiento a mis amigos brasileiros, Evaldo, Luciano, Fernando. No puede ficar fuera nesta. Tem sido muy legal conmigo y toda estar aquí en Río de Janeiro tem sido muy boa. Muito obrigado. Y muito obrigado, Constantino. Okay. The motivation. There are several problems. Oh, how many? 10 minutes. No problem. 10 minutes is sufficient. Okay, the anomalous diffusion is the main motivation of the present problem because anomalous diffusion comes from physics and some problems in physics like conductivity of silicon, where in the semiconductor, the silicon, the conduction is on the phonon, not electron, where the mean free path is not too short. Another problems are related to ion exchange in glasses, for instance, where in the first problem we have to an equation called the porous media equation, and in the second problem we have logarithmic diffusion, and there are another problem like overdamped regime where Evaldo, Constantino, Fernando, they are studied so much this problem, and in this kind of problem we have a quadratic diffusion law. Regarding some population problem, we have some rabbit that are so happy because they find some carrot. They invite other friends about to eat this carrot, but together find more carrots. This problem is solved by the Fisher-Kolmogorov equation like this. There are another approach, but we are choose the Fisher-Kolmogorov equation. In 2019 in Chile, there are social outbreak. This is a photo in the center of in the downtown Santiago. But when this occurred, I I thought the following. There is a superhero that can explain this problem. Who is it? The generalizator, as said yesterday by Hans. No? In this case, we are remarking some social context and social claims about retirement, education, health care, and a claim, an ideological claim, inequality, maybe a more elaborated claim as inequity. But the life quality is not totally related to the wealth production in general. They are in other direction. According to relative deprivation theory, we have some income inequalities, and the well-being perception are not related or are related, weakly related over them, because inequalities, the perception of inequality affect the well-being perception. This was advanced in this paper where we work with Diego González, worker of Banco Itaú, but Itaú Chile, and Carlos Calderón, as psychologist devoted to the social psychology. And in this case, we take some parameter, macroeconomic parameter like consumer price index, the gross domestic product, and the employee distribution, the income of the employee distribution, and the per capita income distribution. These four parameters and data we take and put in the Fisher-Kolmogorov equation, and we obtain some interesting results. Mapping the social outbreak into the population dynamics, we take the rabbit as the product and service, like car, like telephone, but like other necessity that we need to in this context satisfy. And the carrot are our salary. Okay, in this case, the rabbit to eat some carrot. This product and service eat our salaries. This is in the Fisher-Kolmogorov equation in the following sense. Some useful distribution are like the income and per capita income. This is the income of employees or workers, and this is per capita income. The per capita income is the result of the Fisher-Kolmogorov equation, and the worker income are the potential inside in the Fisher-Kolmogorov equation in a sense that we put here. Another parameter are the GDP and the CPI, where we put in the Fisher-Kolmogorov equation in this way. This is per capita income. We have the working income and the GDP variation, and CPI, that is a variation as well. Some result, we have the stationary numerical solution we obtain two behavior in this kind of solution. The behavior that the maximum travel to zero and where the maximum travel to positive values of x, where x are income, okay? We have here an analytical proposal because we need to solve analytically. This proposal is the following, where a similar distribution of income can be put it here by this law, a quadratic law. Okay, we work with this. This is a variation of the system, but this is the possibility that we have here, that we need to do it to obtain analytical solution. Okay. Okay. We relate the perception dynamics with the dynamics of the maximum of the distribution that result from the Fisher-Kolmogorov equation. When H2 is negative, the solution is bad because Y, the perception dynamic, travels to zero. And then the perception of the population is that more people is living with less money in time. When H2, the concavity of the parabola is positive, generate a well-behaved solution because the perception of the population is that the more people is living with more money. Then, in conclusion, the connection between several physical and social problems can illuminate new knowledge in every field. The Tsallis distribution helps to solve analytically the nonlinear Fisher-Kolmogorov equation to support several problems in complex systems in these cases. The answer maximizes the general form of the Tsallis entropy, and the additional solution can be helpful to discuss another type of problem. But when we apply only in the social system, we need the answer that maximizes the Tsallis entropy. Consequences to public policies. Our result lead to propose public policies taking into account the following. First, the interval between the minimal and maximal incomes is a relevant parameter that introduces concepts such ethical income that we discussed briefly in our paper. This measure can decrease inequality. However, the maximal and minimal are not relevant if the shape is not manipulated as well. We need to manipulate the shape of the distribution, not taking a maximum. We need to observe a minimum. Employee income need to define according to this kind of situation. The concavity in general needs to be positive. Okay, a single peak where absolute equality of income is a very bad result, represent a collapsing of the economy and adverse effect on per capita income. Future, we study parameter as the variation in time, how this result are modified. We consider other macroeconomic parameter as the debt. We are coupling as well two Fisher-Kolmogorov equations to study this problem. Yesterday, one of my students presented this a poster with this idea. Studies some other problem with nonlinear diffusion equation is advanced as well with another student. Papers, collaborations, the student, they are in the room, and a mention of Angel Ricardo Plastino, who is supporting our research. Thank you very much, permanently. Thank you. Thank you.
Any question? Okay, so let's, oh.
Let me tell you something about Sergio. When Spain conquered from Mexico to the south of Argentina, everywhere in Latin America, excepting Brazil, which was conquered by Portugal, the Spanish defeated from the Aztecas, Incas, and everywhere, but they could not defeat the south of Chile because there were the Mapuches. And the Mapuches were terrific warriors, and the Spanish could not defeat them. For those that know places like Bariloche, where there is a very famous lake, Nahuel Huapi, those words are Mapuche. And many other places in Argentina and Chile are referred to with Mapuche language. So in Chile, there are a few doctors in physics whose father is Mapuche, but not the mother, or whose mother is Mapuche and not the father. And there is only one whose father and mother are Mapuche, Sergio Huichalaf Kurilev.
Yes. Thank you very much.
So the next speaker is F.R. Ribeiro. Yes. Who is Ribeiro?
I think Ribeiro didn't come. Mr. Ribeiro? Fabiano Ribeiro. Okay, then we'll go straight to my talk.
So you are going to talk now, Fernando?
Yeah.
Great. Okay. Mas Fernando is going to speak now. Vai mudar, Evaldo vai falar às 4. Você sabe colocar aquilo, né? Eu também não.
Eu acho que tem que fazer. Vou colocar isso aqui na minha, da minha camisa. Eu vou colocar no bolso. Hello? Okay. The pointer. Como usa isso? Fala aí como é que é.
Ponteira para frente e para trás.
Assim na ponteira.
E aqui é para frente e esse aqui volta.
Rogério. Tá funcionando. Aponta aí.
Ele é vermelho. É porque ele é vermelho, ela está na rua.
Ah, yes.
Porque a primeira é vermelha.
Okay. So what I'm going to talk about is a work we're doing with Constantino and Henrique. Today, I became aware that I'm the second in the rank done by Dennis. So this is the latest collaboration with Constantino. And I'm going to catch Luciano. Vou lhe pegar. In the rank of collaboration with Constantino. This is the latest collaboration. But Constantino has been a very important person in my scientific career. Here I have the my first publication. Here we have the AC, which has passed away recently. Myself, Constantino, and Luciano. This is my first paper in my career, scientific career. At the time that Constantino used to go very frequently to Natal, where I worked before coming to CBPF. And this was my first publication. And so what I'm going to talk today is my latest work with Constantino. And during my scientific career, I became the second collaborator with Constantino in the ranking done by Dennis. Okay. What I'm going to talk about is something is something it's very old. It's about Fourier's law. Essentially, Fourier's law states that the rate of heat per unit area is proportional to the gradient of temperature with a minus sign, minus gradient of the temperature, so that heat flows from a heat reservoir with higher temperature to a heat reservoir with lower temperature. Okay, this was published by Fourier at 1822. This year is very important for the Brazilians. We all know this, but maybe the non-Brazilians don't know what this means. I'm going to tell you about what happened in this year, 1822. The Portuguese royal family, a few years ago, have run away from Portugal, running from Napoleonic invasions. They came all to Brazil, Rio de Janeiro, and many rich families of Portugal came here at this year. And so after some time, after Napoleon was put in prison, and then the Portuguese recovered the power, 1 year before this, the King of Portugal came back to Portugal and said to his son, "You're going to stay here, you're going to proclaim the independence of Brazil." So that happened 1 year after the King of Portugal left Brazil. And our independence of Portugal was proclaimed by the son of the King of Portugal. And the son of the King of Portugal became the first emperor of Brazil. That's how we became independent of Portugal. Okay? And all the rich families of Portugal, many of them stayed here in Brazil with the first emperor of Brazil. This happened in this year, 1822. That's the year. That's when Fourier published his important book, The Theory of Heat Theory. And Constantino told me a few days ago that the paper of Fourier was rejected at first, at the first magazine that he submitted.
During many years.
During many years, the paper of Fourier was rejected. That's so. I'm going to deal with a one-dimensional system. I'm going to deal with a one-dimensional system. So that's the Fourier's law for one-dimensional system. And kappa is known as a thermoconductivity. It depends only on the temperature. If for a one-dimensional system size L, the thermoconductance is directly related to the thermoconductivity, like this. It depends on the temperature and on the length. So here I show you the behavior of the thermoconductivity of typical materials versus temperature. As you can see, good thermal conductors are also good electrical conductors, like here's in Portuguese, copper, gold, aluminum. All these have good thermal conductors. And here are the bad thermal conductors. water vapor, air, see? And they have a well-behaved functions of the temperature. Okay, now 200 years after Fourier holds for large variety of systems like coal, rocks, coal fields, two-dimensional materials, but Fourier law is violated for some systems which at the time of Fourier, they didn't exist, like silicon nanowires, carbon nanotubes, low-dimensional non-scale systems. So theoretical and computational investigations in many particle systems are still being done for investigating the validity of the Fourier's law. So in this work, we investigated a system of microscopic constituents, the classical nearest neighbor interacting Heisenberg rotators. This is the Hamiltonian. Antonio is very familiar with this system. It's Heisenberg rotators, classical rotators. Okay. Three-dimensional. They have three components. And we introduced this kinetic term because we want to do to have equations of motion and to do molecular dynamics, do integration of the equations of motion. We don't want to use any statistical a priori. This is just integrate the equations of motion. This is the system, and the heat should flow from this reservoir to this one. This is the hot reservoir. This is the cold reservoir. Okay? The first particle we put in contact with this hot reservoir, and the last particle with the cold reservoir. There are equations of motion to be integrated. These are easily found. Antonio knows that. And for the rotators at the extremities, we introduce a Langevin dynamics, defined here, through a Gaussian white noise for each Cartesian component. Okay? So this is the system we are going to deal with and integrate the equations of motion. There is a continuity equation for the energy at a given site is given by this. And we look for results at a stationary state. But this is zero, so the heat flux is essentially constant. Some details of the simulations. We fix the two temperatures of the reservoirs, and we call the temperature T as arithmetic average of these two temperatures, and we have chosen this quantity epsilon as 0.125. And the temperature is going to be varied from 0 to 3.5. This is the integration time step, where people who deal with these kinds of simulations know that the smaller this quantity, the more precise the results, but also the longer the simulations. So we had essentially a transient time of like this to reach the stationary state within 3 decimal digits at least. These simulations are done very carefully by Henrique, which should be here somewhere. And here are the first results for the thermal conductivity. I remind you that the thermal conductivity should not depend on the size. So we have a dependence on the size here. And for higher temperature, you don't have dependence on the size. Okay? So how do we interpret these results? There is a crossover. There is a crossover typically for t equals 0.3. Essentially 1, 2, 3 here. Okay? And between the low temperature regime, where kappa scales with L for temperature going to 0, we attribute these results to a classical model. This is a classical model that should not work for very low temperatures. This is a problem of the classical model. And at the high temperature regime, we have thermal conductivity scaling St to the minus 2.25. The thermal conductance, this one should depend on L. And since kappa, the kappa we found is depends on L, increased with L, so the thermal conductance does not depend on L in this region, but here it depends on the size at the high temperature limit. Here I introduce some well-known functions within the non-extensive statistical mechanics. Here's the Q exponential. This is defined only for this argument positive. It's 0 otherwise. There is a stretched Q exponential, an exponent eta here, for eta between 0 and 1. And here we define a shrinked Q exponential distribution with eta greater than 1. Okay, it's the opposite of the stretched Q exponential. Why do I define this? Because the values of eta we're going to find are greater than 1. The fittings we're going to apply are for eta greater than 1. So this is the fitting for the thermal conductance. We have a full data collapse here with this function, which is essentially a shrinked Q exponential. See the value of eta here, this value of eta is 2.88 here. Okay? It's a beautiful data collapse with this function. So these are the numbers we have obtained for the data collapse with the arrow bars. Here, X depends on L also, where you have defined the quantity X, L to the gamma. And our criteria for validation of the Fourier's law is that either the thermal conductivity should not depend on L, or the thermal conductance should scale with 1 over L as high temperature, or L going to infinity. We have, our simulations have shown that if you consider L smaller than 50, then this does not hold, but all this scaling starts to hold for L greater than 50. So this criteria for validation of Fourier's law is a combination of the exponent eta of the shrinked Q exponential, this gamma that appears here in X, and Q minus 1, which is the fitting of the Q exponential. All this should be equal to 1. If this is satisfied, then sigma scales as L to the minus 1. That's what we want. This is the criterion for validation of Fourier's law. And that's what we found for the Heisenberg. And finally, my conclusions, that Fourier's law is validated for a system Heisenberg n equals 3 rotators in d equals 1 dimension. And why does non-extensive statistical mechanics applies to such a simple system as a one-dimensional ferromagnetic Heisenberg model? It's an out of equilibrium regime. That's the explanation we have for this. Because non-extensive statistical mechanics has been applicable to many out of equilibrium regimes. And in our case, we have an out of equilibrium regime. And previous works have validated Fourier's law for XY. That means n equals 2 components in d equals 1, 2, and 3. This was done by Enrique, the guy who does all the simulation. He presented a poster yesterday. So we have a general condition for the validation of Fourier's law, which is here, where all these quantities depend on the number of components for the rotators n equals 2 or n equals 3, that power gamma that appears on X, and the exponent Q, or the Q exponential. That's the general condition for Fourier's law. Okay, so this work is submitted for publication, and I'm going to decrease my gap from Luciano with this. And I would like to thank you all for your attention. Thank you.
Questions?
Thank you very much, Fernando, for your talk. I just wanted to ask you about this new stretched Q exponential and shrink Q exponential. Do these new functions behave as Q exponentials with a different value of Q in the large X regime?
I didn't understand your question.
For X going to infinity?
Yes.
My first guess is that stretched Q exponential is a Q exponential with a different value of Q. Isn't it true? It's a polar law decay in any case. But for large x, it's a power law.
It's a power
so
law,
it's a q exponential with a different value of q. Behaves as a q exponential.
Thank you. Just, I suppose this Q exponential to describe the Fourier's law is a solution of a deformed differential equation. Do you have equivalent differential equation or Q differential equations to describe, in that case, heat conductivity? No?
No,
the Q
there should be a differential equation for where this function is a solution.
Yeah, but you have that, no? Did you explore this? It's a kind of new derivation of heat conduction, but using not ordinary derivative or something like this, but maybe a deformation of the derivative.
There should be
I suppose,
a
yes.
differential equation
Yeah.
for that.
Did you explore that?
No, we didn't explore that.
Thank you. Ordinary. But that means there is a kind of other terms. It's a kind of differential equations on a manifold.
Well, I don't know the full answer of your question, but part of it, there is a relatively simple ordinary differential equation with full solution in the differential equation.
Sorry, Fourier is calling me.
Any other question? So then let's have coffee and come back for the last. Oh, yeah.
Tal. Peraí.
Yeah, yeah. We have just one session is for by Evaldo Curado, but before that, Luciana is going to say some words. Before Luciana, I also want to say some words. Yeah, I know. I just want to thank Constantino once again for the great person he is, not only an excellent physicist, but also a great human being. I was really so touched by, all what he did for us. I came from Recife. I did my undergraduate studies there, my master. And maybe some of one know that is the most neurotic department of Brazil. So to come from Recife to here was to live, I left hell and I arrived in paradise. It is true. It is true. Yeah, I remember, just 1 minute more. The first paper we did together was in the Statistics. Yeah, and I remember Constantino say, yeah, it's a very beautiful paper because Constantino likes beauty. There are several generalizations. If you do go this dimension, you do that. And a few months ago, he sent me a paper, said, this paper is also very beautiful and reminds me of the work we did in the Statistics. Remember? Yeah, so, and after that, I worked on Kels. And it was so nice. It was so great. Yeah, thanks, Constantino. Okay, it's now you.
I don't need it. Good afternoon. Boa tarde. I was not supposed to speak in this meeting, but I took the opportunity to speak some words and some jokes about Professor Constantino, but I have excuse because I'll speak in between 5 and 10 minutes in Portuguese, okay? Because it's very difficult to translate jokes to English. I don't know how to do this. Then you and 2 or 3 more, but it's not so. Okay. These are Ponta Negra Beach. Constantino was open to. Era frequente ele subir essa dona aí, quando ele era muito jovem, eu e ele, né? Subíamos todo dia, né? Ponta Negra Beach. O título é Constantino, nordestino do bom, muito strong man, strong guy, ok? Após a Segunda Grande Guerra, muitas famílias europeias se mudaram para a América do Sul. Penso com a de Rush também, né? Rush está por aí, né? O pequeno Constantino, então, com 3 anos e meio, junto com a sua família, Tsallis, veio da Grécia e se instalou em Mendoza, na Argentina, lá no pé da Cordilheira dos Andes, né? Onde fez os seus primeiros estudos. Ele vem de uma família de pessoas bastante educadas e influentes. Para se ter uma ideia, o seu pai, um comerciante do Mediterrâneo, falava 8 idiomas. Não é mole não, né? A sua tia e o seu avô foram ministro da Previdência Social da Grécia, enquanto seu tio foi ministro da Educação. Não podia dar errado, né? Ele fez graduação e mestrado no Instituto Balseiro, em Bariloche, lá no Centro Atômico Bariloche, que alguém falou ontem aqui. Vale lembrar que na Argentina eles têm um concurso nacional anual que escolhe 15 estudantes para entrar naquele instituto. Após concluir o seu mestrado, ele se muda para a França para fazer o seu doutoramento de Estado, que terminou em 1974. Incluindo o tempo de doutoramento e de professor em Paris,
Ele ficou 8 anos na França. Naquele momento, ele achou que era chegada a hora de retornar para casa. Certo dia, ouvindo uma música brasileira, ele olhou para a família e disse: um país que tem uma música dessas deve ser um lugar muito bom para se viver. Assim, em 1975, ele chegou em Brasília, para sorte nossa, não voltou para a Argentina, para ser professor na UNB. Não resta nenhuma dúvida que isso foi muito bom para o Brasil, né? Naquela época, os tempos em Brasília não eram bons. Tinha general passeando de cavalo lá no campus, não é isso? Aquele clima era altamente desfavorável para um cientista, né? Que é uma pessoa que pensa independente, né? Por conta disso, ele se mudou aqui para o Rio de Janeiro, para o CBPF, em 1977. Por uma coincidência do destino, eu vim de Natal em 1977 e a gente se encontrou no curso dele. Tá? E eu me dei bem no curso dele. Perguntei se ele, a uma certa altura do curso, eu perguntei a ele, eu perguntei a mim mesmo, eu digo, vou fazer meu mestrado com esse cara. Aí eu, um dia, encontrando ele, eu digo, professor, o senhor podia me orientar? Aí ele disse, quando acabar o curso, você faz essa pergunta. Né? Aí, quando acabou o curso, eu digo, e aí, professor? E agora? Vai poder me orientar? Faz esses cálculos aqui. Aquele 77, 78, não fui para Natal. Fiquei nos 40 graus aqui, no calor infernal, fazendo as contas que ele passou, e ali surgiu uma publicação. Quando eu fiz a publicação, ele disse, agora você pode ser meu aluno de mestrado. Ele veio lá do doutorado de Estado da Europa, onde lá era duro pra caramba naquela época. Sofreu, né? Aí veio com essa maneira de ser aqui para o Brasil. E eu sofri. É bom que se diga que hoje era uma mãe. Hoje era uma mãe, comparado com aquele tempo lá. Né? Quando ele veio para o Rio, trouxe o grupo que ele tinha lá em Brasília. Evaldo está por aí, né? Está ali Evaldo, Darli, que estava ontem aí, Ivan, Cid. E tinha mais que talvez não veio, né? O grupo acompanhou ele sem saber se tinha bolsa, sem saber se tinha nada. Vocês foram corajosos, né? Agora eu vou falar da ligação dele com o Nordeste. Deixa eu ver se eu passo aqui. Aí está mais ou menos o roteiro dele, tá certo? Que ele veio para a Argentina, lá da Grécia. Tem umas fotos aí da Grécia. E ele veio aqui para Mendoza, né? E depois para o Instituto Balseiro. Então, agora eu vou falar da conexão dele com o Nordeste, tá bom? O UNB, CBPF. Vocês estão vendo aí aquele trabalho que eu falei primeiro, para poder ser aluno dele, está lá, tá certo? Do Brasil, o Jural fez. E aí está uma série de outros trabalhos, ok? Constantino foi professor, orientou 6 teses de doutorado e 2 de mestrado de professores de universidade nordestina. Ernesto, vou começar em Salvador. Ernesto Borges de Salvador, subindo mais, André de Souza em Aracaju, mais um pouco Uriel Costa de Maceió, mais um pouco Conceição de Recife, pula Paraíba, eu e Ananias de Natal. Co-orientou comigo a tese de doutorado de Samurai Gomes de Aguiar. Okay? Ele tem colaboração científica, pós-doc, papers, com vários membros do departamento do Nordeste. Eu não tenho tempo para falar, porque eu pedi aqui um pouco de tempo. Né? Ele já foi membro, ele foi professor visitante do nosso departamento lá em Natal, 89 a 91, para sorte nossa, né? Em 97, juntamente com o professor Liaci Lucena e outros professores, organizou em Natal um evento internacional chamado Workshops on Foundations of Statistical Mechanics and Thermodynamics. Antes, a gente nunca tinha tido um evento desse porte. Naquela época, atraiu pessoas como Roger Menard, Van Kampen, Henk Hilhorst, Per Bach, entre outros. Com a parceria do grupo de professor Tsallis, temos aprovado vários projetos de pesquisa, entre os quais CAPES, COFECUB, PRONEX, Projeto Nordeste, entre outros. No atual INCT, tem vários pesquisadores nordestinos, que uns estão aqui, outros já foram embora, mas são muitos, né? Com a colaboração do professor Tsallis, envidamos esforços para criar em Natal um Centro Internacional de Sistemas Complexos. O projeto seria criar um centro multidisciplinar, a exemplo do que ocorre em vários lugares avançados da Europa e dos Estados Unidos. Santa Fé Instituto, por exemplo, né? O nosso sonho ficou muito próximo de acontecer, não foi? Isso é outra história. Mas, por causa dessa ideia, aquele centro de Brasília, ficou todo mundo brigando para receber, que ele saiu de Brasília, Natal já estava pronto para receber, e o Instituto Internacional hoje está em Natal, num certo sentido, você foi responsável para criar esse caminho. Né? No dia 15 de fevereiro de 84, ele proferiu a aula inaugural da UFRN sob o título Por que pesquisa na universidade? Recebeu o título de doutor honoris causa em 2006. Um dos seus maiores amigos foi um nordestino, o saudoso professor Ricardo Ferreira, de Pernambuco. Teve um episódio aqui, neste centro, no CBPF, Constantino foi obrigado a mostrar que tinha coragem. Tá certo? Ele, num certo sentido, não quero entrar em detalhes, teve uma briga aí com um professor, né? E, ao sair do elevador, Ricardo Ferreira encontrou com ele e disse: você não agrediu, você se defendeu, porque nos vales secos da Grécia e no sertão do Nordeste, ninguém leva desaforo por acaso. Foi ou não foi? Né? A amizade só foi amarrada, né? O professor Tsallis adora tapioca, queijo de coalha, música nordestina, lambada. Ele deu aula de lambada lá em Natal. Vocês acreditam se quiser. Tá certo? Por que não dizer que ele é um autêntico cidadão nordestino? Né? Além de muitas contribuições na mecânica estatística tradicional, o professor Constantino tem se dedicado, nos últimos 35 anos da sua vida, a uma nova teoria que se aplica a sistemas complexos, que é a mecânica estatística não extensiva. Pelé fez mais de 1000 gols. Ele deu mais de 1000 palestras internacionais. Já é uma comparação boa. É o Pelé da física, né? Eu dizia assim. Vocês olharem esses papers aí, em geral, aí tem só uma pequena fração, porque eu mesmo sou o cara mais conectado a ele, vocês viram hoje de manhã, né? Se eu for botar aí se eu for botar os papers todos aí, umas 5 páginas aí, tá certo? A sua filha mais nova, a mecânica estatística não extensiva, atingiu a maioridade, professor. Saiu do seu alcance, saiu do seu controle. Está galopando sozinha pelo mundo afora. Né? Professor Constantino, quem sabe ela não retorna para convidá-lo a dar uma volta lá pela Suécia? Né? Who knows? Decidiu eu quero ir junto. Né? Essa viagem para a Suécia, who knows? Né? Tive a sorte de te encontrar na minha vida. Obrigado, meu mestre. Agora eu vou saudá-lo como fazem os japoneses, que eu adoro aquela saudação. Professor Constantino, arigatou gozaimashita.
Great, 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 great. Now, Evaldo's turn.
Okay. Water. Hello. Lucian is a great scientist, but I'm sure that if he is also a great actor, and if he works in theater, he will be a success, I'm sure. Okay, bom, let me talk about this work. And you see here, Constantine is there. It's not working. Okay. Steam not working. Esse aqui? It's coming. Okay. 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 Thank you. Well, Constantine is here, and this is make this work very interesting and important, because this is one of the few works of Constantino in the last 30 years that's not about Q statistics. So only the fact that he is interested in this topic is interesting. And well, I met Constantino first time, not so far, but for a long time, only 48 years. But I'm not the oldest one. Jean-Pierre knows him before me. And I met him in 75 in Brasilia. It was at undergraduate course at UNB, and he arrived from France. And it was hard times at that time. Luciano said it was a military dictatorship, as you know, many countries in Latin America, also even in Europe at that time. Spain also was a dictatorship, but well, it was difficult in political sense. But there is a funny history that I would like to tell, is that the military put some spies in the campus to observe teachers and students, to make reports to the intelligence, military intelligence. But after a few, not so many times, everybody knows who were the spies. And one professor, when Constantino arrived, said to him, "Oh, look, this guy there. He is a spy. Take attention with him." And when Constantino was giving his first class in Brasilia, who was sitting in the first line? The guy was there to observe the new professor that arrived. And Constantino was advised, so he knows. He knew. And what he did, he gave the class, and then he said, "I will change my way to present this talk. I will call someone to give some calculation in the blackboard. Please, you calculate the partition function of a spin 1/2. Obviously, he have no idea how to do this. And Constantino was advised, so he knows. And what he did, he gave the class, and then he said, "I will change my way to present this talk. I will call someone to give some calculation in the blackboard. Please, you calculate the partition function of a spin 1/2. Obviously, he have no idea how to do this. And
And nevermore he was in the class after this first day. Okay. But okay, then as Hans said and Luciano also, he moved to Rio, and we start in 75. There was a strike, 77 at the university. He was invaded by the military and many professors go out from Brasilia. And Constantino came to Rio because it was almost impossible to work there. And then we were 4 students that started to work with him, the master. And 4 students, we have no possibility to continue doing papers. There were only 3 PhD professors after the exodus of all the others. So the 4 were Ivan. He worked in Londrina, and now he's retired. Now he's write books on poetry. And Sydney, I don't have the picture of Sydney. Darlie and Evaldo, I don't have the picture of these 3 also. Evaldo, they said that he has not WhatsApp. So, let alone photos. And Aglaé, he was here on Monday. And then, there are 5, the first students of Constantino here at CBPF. And then arrived the Nordestinos. Nordestinos were Ananias. Ananias, I don't know if how is there. From Natal, Luciano, you know very well. Uriel is not anymore among us, fortunately. And Raimundo, Alexandre. And, and then many others later come, Conceição, Daniel, and many others come here to work with Constantino, with our group also, with Aglaé and me, but we work here also. And then this is the first paper I published with Constantino. It was in 80. It was a normalization group using this was a new technique at that time. This is the second one. These 2 first papers, and this is the last paper we published last year about the relativistic gas. As I said, this one of the few papers he published not related with Q statistics. And Constantino and me, but Ivan and Carlos are they are relativist people. They work on relativity and cosmology. So it's a mixed paper because we mix statistics and relativity, and so it's good to have people from both sides. Okay, let me talk a little bit about this. So this is a nice problem, as Jean-Pierre also talked about yesterday or yesterday, I don't know. This is an old problem, more than 100 years old, and it's not solved yet. So we have many propositions, and this is very nice. It's very good to have many possibilities because in one moment this will collapse in one, but at the moment we have many, and this is one of them, one more. So I will talk about Maxwell and Newton. I will talk about our proposal and some molecular dynamic simulations we have done. So this is Maxwell. He presented his distribution in 1859 And he published his paper in 1860, 1 year after, but he presented first in a conference. And this was the first time probability enters in a physical theory. Up to there, it was only deterministic equations. This is the paper where he published. This is the paper. You see here is page 19. And in page 22, he starts the demonstration of his distribution. And you see, you have any particles, and x, y, and z are the velocities, not the positions. It's a strange notation, but it's like this. X is the velocity in the x direction, for example. And the number of particles for x between x and x plus dx is a function to be determined, dx. The same for the other directions. And then, as these probabilities are independent because the directions are independent, the total number is the product of the three probabilities. And this reasoning here is nice because if you suppose that any particle starts from the origin of the same instant, then this will be the number in the element of volume after unit of time, and the number will be this one. But this is very nice. The directions of the coordinates are perfectly arbitrary. The x can be like this doesn't matter. So this cannot depend specifically on x, y, etc. It depends only on the distance from the origin. Because it depends on the distance, I can put my coordinate x as I want, and the result will be the same. So this product here is in fact a function of the distance. And then the solution of this equation is the Gaussian. This is demonstration of Maxwell, 1 page. You see the influence of this very small demonstration. I show you all the demonstration here. And the impact of this is up. Huh?
How many pages?
No, it has many pages, but the demonstration is this size, only this. He discussed many other things, for example, mean velocity, etc. But the demonstration is with these arguments. And okay, so this had a very big influence because kinetic theory was disputed at that time, but many people believe in kinetic theory of gas, for example. And then with this possibility open mind in that time. And for example, Boltzmann used this to study the evolution time of distribution of velocity of gas. This was an idea that came after this demonstration by Maxwell. And this is we are now in 1872. And Boltzmann published this paper. It's a horrible paper, has 94 or 95 pages, and worst, written in German. And but here you have the Boltzmann equation and the so-called H theorem in this paper. So it's not true. This is the paper, you see, written in German. And here in some page there, he developed his equation. He showed that this equation arrives at a stationary state that is the Maxwell equation, the Maxwell distribution. So he showed this, and he proposed this equation here, that which we call now H theorem, but he not called H, he called E. So for entropy, that was called by Clausius a few years before. Clausius was 65, 64, I don't know. And who calls this H was Barbary, Samuel Barbary, some years later in 1890. And then everybody calls it H theorem, but it was proposed as E theorem. Okay, it's a curiosity. And but you know, physics is movement, science is movement. Religion is static, but science is movement. Né? So the theory proposed by the distribution proposed by Maxwell, when Einstein published his special relativity, né? You cannot have a particle with velocity higher than c. So the Maxwell distribution is wrong at high velocities, because even if it's so small, you have a small possibility to have particles with velocity higher than c. And then, so you have a limit velocity. So it's not possible to you have to modify anyway the Maxwell distribution for high velocity. Né? And then Eutner, Frank Eutner, was a postdoc of Max Planck. Max Planck gave to him this problem, tried to adapt the Maxwell distribution to special relativity, a simple problem. Huh? And he published his paper in this year. And the idea of Eutner is following. Let us consider a volume element in a space. Here, X is really position, it's not like Maxwell. And rho, these letters here, are the relativistic velocities. And then he proposed the entropy with some distribution function, and the energy that is also in this element of volume, this relativistic space, a flat space, you see here. So the differential number, a small number in this volume, the number of particles in this volume, given by the distribution, is if you extremize S, take into account this constraint, you have this distribution here in this space. Okay, in this space of. But now Newton said, I'm interested not in the relativistic space, but in normal space of velocities. So X, Y, né? And here is velocity. So you have to change from this element of volume to this element volume of velocities. When you do this, you calculate this transformation from d omega to d sigma. It appears a factor gamma 5. Gamma is this traditional expression here. No, this is for 3 dimension. If you do this reasoning in d dimension, here you have gamma to power d plus 2. So if d is 3, you have 5. Okay. So you have this relation. And this is distribution of Eutner in 1 dimension is d plus 2. So in 1 dimension, you have gamma 3. And this is the distribution of Eutner in 1 dimension. This is a normalization factor, Bessel function. And d dimension, you have this factor here. And here is essentially the factor, the relativistic energy. Né? So, but the space of velocity is not flat. It's a Lobachevsky space, has a negative curvature. So the correct factor, prefactor that you have to respect this is a factor gamma to power 1 plus d, not 2 plus d. So this factor is wrong. And also, you have also here that you can try to eliminate doing a trick like Jean-Pierre showed, to make a multiplication by 2 quadrivectors. So you can, in some sense, eliminate, but this you cannot eliminate. So Eutner is not a Lorentz invariant distribution. Okay, let us see alternative proposal. This was done by Hangi and his group. And he said, okay, this prefactor is wrong. So let us modify this prefactor by hand, between 1 plus d, by hand. So we adapted this. He called this modify Eutner distribution. He published this physical review letters in 2007. There is an intense debate about this. And from relativistic one-dimensional molecular dynamic simulation, and they said that the numerical evidence unequivocally favors the Eutner distribution. So it's not a large invariant, but it favors, so it's a crazy thing. But okay, this is simulation he's shown. In one dimension, to redistribute the energy, you have to consider 2 types of particles, light one and heavy one. And this is the simulation. This dashed line here is the modified Eutner distribution. The other one is the Eutner distribution. So it agrees well with Eutner, not with the modified Eutner distribution. Okay, so we have a problem. But let us show you another proposal that is simpler. This is in one dimension. This is the addition of relativistic velocities, okay? You know well. This can be written this other way, more symmetrical way. These 2 equations are exactly the same, but that one is written in a symmetrical way. Okay. So this can be generalized if you have more particles. And if you take the logarithm of on both sides, you have the logarithm of this equal the sum of logarithm of this. And but this variable here, logarithm of this, is known as rapidity in relativity. And this is a variable that is has the property that is along one dimension, you can sum it. And it varies from minus to plus infinity. This rapidity here. So this, you see, from the addition of velocities, you arrive changing this just manipulation, algebraic manipulation, you arrive at this sigma is a sum, simple sum of variables that go from minus to plus infinity. So you scale this sum with square root of n. This is the proper scale you have done. Otherwise, you don't get this. You get an exponential if n is large enough. Okay? So by central limit theorem, you have the exponential. So if you write back s as a function of sigma, you have this equation function of sigma. And if you use the relation of sigma with velocity, you have a distribution in function of the velocities. You have here the factor gamma 2. We are in one dimension. So 1 plus d. If d is 1, you have exactly 2. What exactly we have here? This comes from this relation. So this factor comes naturally. And rapidity is a Lorentz invariant quantity, so this is a Lorentz invariant. The aspect is like this. If energy is small, you have a kind of Gaussian. But if you increase the energy, the green one. If you increase more the energy, you have a kind of 2 peaks in the my plus or minus C. Né? This is a Lorentz invariant distribution. Beta is should be a invariant quantity. So we have this. We can write this way on a scalar adimensional parameter. And T is the temperature. Né? When you take beta like this quantity, and you take V over C going to 0, you recover the Maxwell Maxwell distribution. So T is a Lorentz invariant quantity, unlike the Jean-Pierre presented in his talk. And obviously, this is limited. You cannot have, you have not velocity higher than C. So just to show you that in one dimension, you have, for example, you have a collision, proton-proton, for example, and you have a transversal distribution and a longitudinal distribution. The longitudinal distribution, they plot here the longitudinal distribution in function of y, or y is the rapid distribution, because it's a convenient variable for one dimension in relativity. This is the simulation of the rapidity. Here is the rapidity. You see, goes from minus to plus infinity, so all the real line. And here is the distribution. And for Eutner, light particles don't have particles. And for small energy, they have the same picture, the same graph. But if you increase the energy enough, we have the quantity above this threshold energy, things are different. For example, here, we have the dots, the black dots, black squares are the light particles. The red dots are the light particles. And this is the molecular dynamics simulation. The dots are molecular dynamics simulations. This dashed line here is Eutner distribution. The pink one is the modified Eutner distribution. And our distribution is exactly on these dots. So you have an energy high enough, you can separate from Eutner, modify Eutner, and the distribution I present to you just now. So, okay, I'm almost finished. For example, it's nice to see this energy, but you can put here the several distributions we have. You can put Eutner, you can put modify Eutner, you can put a distribution. And here is this graph. You have energy here in function, here temperature. So for the same energy, for example, here, you have first, you have the temperature for Eutner is smaller than our distribution and is smaller than modified Eutner distribution. So to estimate the temperature of a relativistic in a star, for example, you see the different distributions present different estimates of temperature of these stars. So there is a crossing here, you see, and this point here is very high. It's almost billion of Kelvin. So practically we are in this region here, and this is the scenario. So to conclude, Eutner is not a Lorentz invariant distribution, and we have presented a derivation of the Lorentz invariant distribution based on relativistic law of addition of velocities and central limit theory. And this distribution matches well with numerical simulations, with molecular dynamics simulations I've shown you. It depends on the energy you put in the gas. If the energy is high enough, you can really separate the several distributions. And one conclusion, side conclusion, is the temperature in this scenario is Lorentz invariant. We present the first calculation in 2016, and next year we have also extended this calculations. And thank you very much. And I just would like to finish saying that a sentence by Bertolt Brecht, a dramaturg from Germany. that lived in hard times in Germany and Nazi fascism there, Nazi. And he talked this sentence that was made by political reasons, but you can apply very well for scientific reasons here. And this is the phrase by Bertolt Brecht that I think that fits very well with it was for political reasons, but scientific works also. So thank you very well.
Questions?
Thank you. Thank you for, I understand better now the difference between, you know, the talk you gave and mine, because I followed just the book by Singe.
Yeah.
And it's another
one. Yeah.
It's difficult to make the link because the Singe distribution is concern the momentum, the force momentum on the mass shell with invariant measure Tk over K0. So of course we can translate in terms of relativistic velocity or in terms of rapidity also, but I didn't make the translation. Just
I didn't know this distribution by Singe. You show me.
Yeah.
But I didn't know. That's why we make no comparison with.
We have to make the comparison.
But
yes.
it's interesting to see also to look at how it behaves in rapidity variable
in terms of the rapidity,
very high energy simulation. But I don't know. In fact, we did know. We know these ones I show you.
Thank you anyway.
What would be your suggestion to go to higher dimensions?
Yeah, we are working on that with Carlos, with Ivan, with Constantino. That's the most important case. Mainly 3 dimensions. We are working on that. Carlos is making simulations, the molecular dynamics simulations. And rapidity doesn't work in 3 dimensions in this sense. We have no simple addition of velocity like this one. In fact, it's horrible. The addition of velocity in 3 dimensions is really horrible. We can do nothing with that. But our idea is the following. He already wrote the code, and he's simulating now. And we have to do many, let us say, accurate simulations in such a way that you can see what comes out, and then think about what could happen if you have a good explanation or not for that. But first, we can see what nature, in some sense, because this molecular dynamics is the relativistic law of addition of velocities, tells us, and then we can look for an explanation. We have some insights as abduction, but we want first to see the results from molecular simulation in 3 dimensions and 2 dimensions. We will do both to advance, let us say, explanation. That's what our way to work now. But we are working. We are doing this with Carlos and mainly Carlos. No, the simulation is mainly Carlos from Colombia. Carlos is a researcher from Colombia.
Evaldo, just to be sure, you treat this model as a classical one. I mean, it's a pure classical one.
Pure classical model. No quantum. In fact, if you put Eigenhoff energy, these particles can change. But no, these particles cannot change. They only
they are hard balls.
Yeah, hard balls.
Okay.
Exactly.
Evaldo, I remember that it's like a transmissivity that Constantine presented in magnetic model. It's
Yeah, that's a funny thing because, in fact, I was inspired by transmissivity Ising model to propose this problem. In fact, is this because you have the series and a parallel association, and that's the first transformation when you have the addition of velocities, and you wrote in a more symmetrical way. This comes from an Ising model, transformation in Ising model. You see how the shows are mixture, né? That's funny, but that's one thing inspires other things.
And when I mentioned the composition that Evaldo showed, the rapidity, which actually said the same as David Landau said, it's funny. So Einstein didn't know, but he was solving the Ising model.
One dimension Ising model. The one dimension.
We have time for just one question more. There is any. So
I would like to make a small comment. Is that I was discussing with Constantino during the lunch, and I have a theory and he has a different theory. Because I said to him, when I was 20 years old, I suppose that people with 30 years old more were old people. When I was 40, I suppose when people with 70 was old people. And in 60, people with 90 was old people. So my theory is that old people is always 30 years more than I have. It's my theory. Constantino has a not so good theory that it shrinks. But this is.
okay, so we concluded this nice
Well, thank you.
Stop. Thank you.
Vamos chamar a Ana para agradecer. Vamos chamar a Ana para agradecer. Já foi?
Você quer falar um pouco, Evaldo?
Alô?
Oi, Ana.
Just
Maomé está por aí? Já foi?
a few words. Many.
É para agradecer vocês. Não. Ana.
Many colleagues have asked for PDFs of the presentations. We have almost all PDFs which are presented
aqui, tá?
in this computer.
Depois você vem aqui.
But the PDFs of the presentations were their own computers we don't have. So we would kindly ask those colleagues that presented on their own computers to send to the organizers the PDFs of their presentation, so we can have a complete file of all presentations available to all interested people. We would like to thank the presence of all participants, which came from all over the world, from Turkey, from Italy, from Chile, Australia, US. Okay, we are very thankful to all these participants and also to the Brazilian friends, to everybody. You are part of the success of this meeting. I have to tell you that the organizing committee has done its best to have, so that we had a successful meeting. If anything didn't go according to your expectations, please forgive us. So we would like to thank, does Hans Hermann want to say something? No.
Evaldo want to say something?
No, yes, I would like to only to thank all of you to come here and to say that our group always is like Conceição said, always we work in a friendship atmosphere, you say. Always our meeting have this funny side that is very, very good to work. We don't serious work, but we is amusing also. So this is a funny way, a nice way to work. And you know, you can see this in our meetings. And many people like, we like a lot working this way. So that's it. Thank you very much, all of you.
And finally, we would like to thank our staff.
Yes.
Without them, we couldn't organize anything. Okay. Does anybody wants to say something?
The last chance.
It's the last. Yes. Oh, great. Thank you. Okay, so the meeting is finished. Okay. Thank you very much.